30. Oh, can you hear me?
Yes.
Okay.
Good morning, everyone. So welcome you all to this international conference on the topology in condensed matter system. So today is the second day, and the first session will contain topics related to angle resolved photo-emission. And this session will be chaired by Professor Swapnil Patel from IIT BHU Physics Department. So yeah, please, Swapnil, please start the session.
Okay, thank you very much, the organizers, for inviting me to participate in this conference.
So there is one technical issue or just information. So all these speakers, if they don't want their talks to be available on YouTube, so they can tell us, so we can delete the talks from YouTube.
Okay.
So, yeah.
Okay. So let me thank the organizers for inviting me to participate in this conference as well as to chair this session. Today, we are indeed honored to invite Professor Adam Kaminsky from Iowa State University, who is really an expert in the area of this topological materials and who has had very good record of good work in this area. So we have a talk session of half an hour, completely, which will involve 25 minutes of lecturing and 5 minutes of question answer session. So without spending more time, I'll invite Professor Kaminsky for delivering his talk. His topic of talk will be electronic properties of new topological quantum materials. So Professor Kaminsky, thank you.
Okay, thank you very much for this kind introduction. Can everybody see the screen of the PowerPoint?
Yeah, we can see.
Perfect. Thank you very much. Thank you to the organizers for the invitation, especially for arranging a very convenient time for us to give this talk over the Zoom. I'm going to talk about some experimental results which are primarily obtained within what we call CATS, or Center for Advanced Topological Materials, which is a Department of Energy EFRC, so it's funded by US Department of Energy and involves several institutions from US and abroad. So my collaborators, the ARPES group consists of Ben Shrang, Yevgen Kuroshenko, Kyunchan Lee, Nahyun Jo, and Yun Wu. Samples are provided by Jingyang Yan, as well as group of Paul Canfield, and theory support was done by Lining Wang, Thais Chevas, and Peter Orth, as well as Robert Jan Slager and Ashwin Vishwana. So the brief outline of the talk, I'll introduce ARPES. I think this is probably the first talk on ARPES maybe in this conference, and then talk about several different classes of topological materials. So ARPES technique is sort of well established by now. It relies on shooting an electron onto the sample, extracting shooting the photons onto the sample, extracting electrons, and by measuring the intensity of those photoelectrons as a function of energy and angle, we can find out the primary quantum numbers of electrons, the binding energy and its momentum. So if you imagine some band structure of a material with a valence band shown here in blue, the red conduction band and green unoccupied bands, if we now excite an electron from any point of this band structure, we're going to move it in energy by the energy of the photons. But because there is a work function of a material, this electron outside is going to acquire some kinetic energy. And by measuring this kinetic energy and intensity at this kinetic energy, we will see series of peaks. Every time there is a band encountered by the photon that ejects a photoelectron, there's a peak in a spectrum, and by shifting it down, we can then correlate energy location of those peaks with the bands inside of the solid. This is sort of the old-fashioned way of doing ARPES, where a single curve was measured at the given time. Nowadays, we have a two-dimensional detectors that in a single measurement can obtain a cut through a brilliant zone. So this is, for example, present such a cut. You can see these bright lines of yellow and red intensities, which are the location of the bands. There is this line here above which there is no intensity. This is the Fermi energy. This is yet another of those cuts. And by acquiring data at, let's say, Fermi energy, which is here, and plotting as a function kx, ky, we can obtain a Fermi surface of a material. We constructed several years ago a laser-based ARPES system where we can tune the photon energy between 4.5 and 7 eV. We have a very small beam size, about 15 microns, which is very useful for studying small samples. Just to give you an idea how much of an improvement that is over a synchrotron technique, this is some of our old data on the left obtained from magnesium diboride back in 2003 using synchrotron. And you can see this data is very broad. And to extract gap, we actually have to do modeling to model the sort of shift of the leading edge of the spectra. With the laser system, the data shown in this center frame is actually data from this little green box here. You can see precisely the location of the band. You can see a characteristic kink, which is due to the electron-phonon interaction. And we can, with a high precision, measure the superconducting gap in this material. Such a detailed data allows us not only to measure the gap, but observe other phenomena, such as excitation modes. This arrow here marks this dip in a spectrum due to the interaction of electrons with a collective excitation. We also developed a new way of cooling samples for ARPES. If you would use a liquid helium that typically is extremely expensive, especially nowadays, and ARPES uses enormous amount of liquid helium because of the opening required to deliver photons and extract electrons. We use a pulse tube to reliquefy the helium in situ, so we can actually cool the sample down to liquid helium temperature, and by accumulating liquid helium and then pumping it down, we can go as low as 1.7 Kelvin. This is data acquired inside of the ARPES system. We also have a 4-point contact measurement, so we can actually measure resistivity of the samples in situ while performing ARPES measurements. This is example of indium at a transition temperature of 3.2 Kelvin. Let me just start with something quite unusual. So everybody by now knows about strong topological insulators, but in addition to those, there's another class of topological insulators which is called weak topological insulators. One of the first examples of those was discovered in a group of Professor Takeshi Kondo, who looked at beta bismuth iodide. And so the difference between the strong and weak insulator is the Z2 topological index. For the strong topological insulator, this index is a scalar. It's just a non-zero scalar value. However, in some materials, this index actually has vector components, X, Y, and Z. And if the scalar component is zero, if you have a vector component, such material is called a weak topological insulator. Unfortunately, all the known examples of those are cleaved at the planes that do not display surface states. So the strong topological insulators, any cleaved plane has surface states, so it's very easy to identify those materials. For the weak topological insulators, only certain planes display surface states or edge states. And before, people had to go to great difficulties. In case of the bismuth iodide, you'd have to use a very small beam at the edge of the sample, so cleave the sample at the edge, and only then they could identify the 2 Dirac cones, which demonstrate presence of the weak topological insulator. At some point, when we were sort of looking for new materials, we thought to ourselves, what would happen if you take materials with a lowest possible number of symmetry that you can cleave and perform ARPES? And after a long search, we found out exactly one of such compounds, and this was rhodium bismuth 2. So this material actually has a natural cleaving plane, and it's a triclinic crystal structure. So this is like the lowest possible symmetry crystal we could think of. As it turns out, after a brief calculation of DFT, this material is actually a weak topological insulator. And the best part of it was it actually cleaves along the planes which has surface states. And this is ARPES data and calculation of the Fermi surface. But if you look along the cut from gamma to the zone edge, you can see there is one Dirac cone exactly at gamma, and the second Dirac cone here at the edge of the Brillouin zone. So this presence of even the number of Fermi crossing along gamma to zone edge cut demonstrates that this is indeed a weak topological insulator. Now, this material is actually even more interesting because it has a very large Van singularity, which is located very close to the Fermi energy. So on top here, there's a calculation. You can see 2 overlapping bands, and there's a Dirac point right here. So along one direction, this looks like a Dirac point. It's like 2 intersecting planes. Along the other direction, it looks like 2 parabolas with a minimum located here and here. And this picture on the right shows roughly the representation of band structure, and presence of this saddle point here is evidence for Van Hove singularity. Van Hove singularity are particularly interesting because there's a divergence of the density of states. So if this is present close to EF, you can have all kinds of interesting phenomena. So not only is this material weak topological insulator, but also we can expect, if we can tune its chemical properties by changing the EF, we can actually expect some interesting phenomena such as density waves, or maybe even superconductivity. Let me now move to the magnetic topological semimetals. I think one of the first discovery of such a material was magnesium bismuth telluride, and this compound was a subject of very intense studies over the last couple of years. So the first discovery was done by a Russian group in 2019, and this material was suspected to be axon insulator, which means that the Dirac cone was gapped as a function of temperature when the magnetic order is established. Now, this was a particularly controversial issue, and there's, I think, a couple of dozen papers stating there is actually temperature-dependent gap in this material. There's another couple of dozen papers stating there is no gap that opens with temperature. Our own measurements actually showed that down to 8 Kelvin, we don't observe any gap in the Dirac cone. The data on the right is a second derivative of data on the left, and you can see there is a Dirac cone without any gap present. However, this material has cousins. There's several variants of this material. So this was called MBT124, 147, and 1610. In particular, the 1610 is interesting because you have several cleaving planes, and those cleaving planes occur at a different distance from the manganese layer, the one that carries the magnetic order. So these are the calculation of Fermi surface at 3 different terminations. And to our big surprise, when you actually measure the crystal, it cleaves actually at all of those planes within the single piece of the crystal. So by just scanning the beam along the sample, we can measure data at the manganese layer, 1 layer above or 2 layers above. And the data that we measured in terms of Fermi surface agrees actually quite well with the calculations. Only one of those cleaving planes, the one directly above manganese layer, actually has an observable Dirac cone. So we started looking at possibility of opening a gap in this Dirac cone. And such a gap is observed at low temperature. You can see at 3.8 Kelvin, the bottom part of the cone is separated from the top part of the cone by the gap. And as we increase temperature, this gap is becoming smaller and smaller. Unfortunately, the closing of this gap does not correlate with the magnetic transition temperature, which is about 24 Kelvin. So we don't quite understand the origin of this gap. It looks like it's unlikely related to the magnetic ordering in this material. And just studies of this gap are quite difficult because you can imagine with the Dirac cone, if you deviate just a little bit from the Dirac point, you're going to see sort of separation between the top and bottom of the band simply because of the geometry of the cone. So one has to be very careful about making very detailed scans and always measuring exactly at gamma. At high temperature here, the gap is closed, and as we cool down, the gap is open for all the cuts around gamma. So we can indeed confirm that the gap in Dirac cone opens in this material, but so far we don't understand its relation with the magnets, whether it's related to magnetic order or not. The next class of the interesting topological materials are Weyl semimetals. So the Weyl semimetal occurs when you have a Dirac semimetal and you introduce a breaking of the symmetry, either the inversion symmetry or time reversal symmetry. That's causing the Dirac point to split into 2 poles. The Weyl point, which is positive and negative, those are effectively magnetic monopoles in a momentum space. And several of those examples were discovered primarily for type A, which is titanium arsenide, niobium arsenide, and so on. And there was some prediction back in 2015 of a type 2 Weyl semimetal, and the suspects here were tungsten ditelluride and molybdenum ditelluride. First examples of tantalum arsenide, niobium arsenide was a very famous series of papers, primarily from the Princeton group, where they discovered the presence of Fermi arcs and confirmed with the experiment and calculations that this actually Fermi arcs signifying presence of the semi-metallic state. The prediction for type 2 Biaxial metal, it was more difficult because it was in a material that was very difficult to grow. Molybdenum Telluride was in a special metastable phase, but there were clear predictions of presence of the wave points. And indeed, we were able to obtain those samples and measure them with ARPES. And we observed presence of Fermi arcs connecting the wave points. One of the set of the Fermi arcs is on this side here and here. The second is on this side here and here. And detailed analysis of band dispersion revealed presence of the veil points, which were touching between the bands on the occupied and unoccupied side. The second material, which is tungsten ditelluride, was even more interesting because this material was displaying a gigantic or extraordinary magneto resistance. Resistance was changing by a factor of, I think, 5,000% at low temperature for a reasonable magnetic fields. The Fermi surface of this material is rather simple. It has a sets of hole and electron pockets on either side of gamma. And this is indeed what our measurement reveals. So this is data shows you one side of gamma point, which is the cross line here. And you can see both electron and hole pocket for each of those sides. However, finding the evidence for the Biaxial metallic state was not easy because those samples are extremely sensitive to pressure. So normally, if you measure sample after cleaving, anytime there is a warping of the sample, so there's some strain that destroys the Biaxial metallic state. And typically, the measured data just shows presence of electron in the hole pocket without any topological features. However, you can identify small parts of the sample when the sample was not strained. These are shown by those red dots here on this measurement. And then if you perform ARPES measurement, you still see the electron in hole pockets, but now they're connected by Fermi arcs, which is the evidence for presence of the veil points. If you look at detailed cuts, so these are the Fermi arcs shown here and here, and you can see if you make vertical cuts here, this is nice parabolic, very sharp dispersion in surface state. So this can be a surface state, and it really disappears beyond the veil point, demonstrating that unstrained tungsten ditelluride is a veil semimetal. The veil semimetals we discussed so far are caused primarily by the breaking of inversion symmetry. And there was a long quest to find the veil semimetals, which are a result of breaking of time reversal symmetry, which means presence of magnetic field. And the reason for this is simple, because if it's done by presence of magnetic field, the properties, topological properties of those materials would be very easily tuned. You can apply a magnetic field from a magnet, or you can apply strong magnetic field from a laser beam and switch on and off topological properties of those materials. After some search, we were able to identify one of those compounds, which is europium, cadmium, arsenic 2. And the DFT calculation revealed that indeed this material can be easily tuned by the presence of magnetic order. And depending on type of order we're going to get a different topological phases. So for example, if it's a antiferromagnetic ordering of type A, you're going to get topological insulator. If you're going to have an antiferromagnetic type C, you're going to get a direct semimetal. And indeed, if you apply it, the order is ferromagnetic along C direction, this material will become magnetic topological semimetal. The Berry first calculation revealed indeed presence of just 2 veil points. So this is the ideal type of material because presence of just 2 veil points guarantees that the material will be very sensitive to presence of topological phases. Calculation of surface states reveal indeed the presence of Fermi arcs connecting the veil points, and the veil points are located fairly close to EF, about 48 MeV above EF. So then, of course, the quest to find the actual crystals started. There was some preliminary earlier studies in 2018, and all of those materials that were grown previously show antiferromagnetic order. To our great surprise, the crystals that were grown in Paul Canfield's lab, some of the first samples grown following something different, somewhat different recipe, showed ferromagnetic transition with a critical temperature of 30 Kelvin. So this was a big surprise, and we spent a fair amount of time studying why there's such a difference in magnetic ordering for seemingly the same crystals, as it turns out small amount of vacancies or impurities can flip this material from entothermic to ferromagnetic state. ARPES revealed actually a pretty complex band structure. There are several bands present in the sample, and to our great surprise, it turns out that the ferromagnetic samples and entothermic samples are not differing in terms of doping a lot. There's a small difference of shift of EF, and this is what seems to be enough to make the sample either ferromagnetic or antiferromagnetic. Those materials display this very strong suppression of scattering below the magnetic transition, which is quite known for a while. However, the detailed effects on the electronic structure of these transitions were not known, and this material seems to be like an ideal case for studying this. Indeed, it did not disappoint us. When we cool the sample down across the transition, there are some dramatic changes in the band structure. We can see two primary effects. One is this fully occupied band here is moving down in energy. And second effect, the very broad bands present on the both side are actually becoming extremely sharp. This is cooling from 40 Kelvin to 10 Kelvin. You see all this stuff here, which was a very broad set of bands, now becomes very sharp, and some of those bands actually becoming sharper than the others. So some selectivity with respect to the band structure. The detailed data reveals that things are even more complicated. Suppression of spin flip scattering is actually very band selective. Only few bands, the inner bands here, participate in this process, while the outer bands actually remain fairly broad even at low temperatures. Now, within those bands that become sharp, this sharpening effect, the enhancement of quasi-particle lifetime, occurs only within certain energy range, indicated by the red arrow here, which coincides with the top of this fully occupied band. So it looks like the intra-band scattering here plays a very strong effect, and the only suppression of the quasi-particle occurs is in this part of the band where there's no possible intra-band scattering. This is some more detailed data demonstrating the shift of the fully occupied band as a function of temperature and suppression of the scattering rate. And as I mentioned before, this point at which the suppression occurs is determined primarily by the location of the fully occupied band. Let me finish the talk, if there's a few minutes left, with a section on unidentified topological objects, or UTOs. And we are lucky enough to discover one of those. And I think to this date, there's no theoretical understanding of the origin or the nature of the topological state in this material. Again, this material has this nice property of just gigantic Magneto resistance, where the resistivity is changing by several orders of magnitude upon application of magnetic field at low temperature. The band structure is rather complicated. There's a very strong bulk and surface components. The calculation of those are shown on the bottom here. With ARPES, we actually see combination of those two. However, that specific points near the zone of the bound, brilliant zone. For example, on the top here, this top part is dominated by bulk state. There are very few bulk states on the side. The surface states dominate the side part here, and they are absent on the top. And indeed, we can identify in our ARPES data, those parts on top here are primarily consistent of the bulk states, which are very broad intensity in between the bands. And if you look at the horizontal direction, the data is very sharp, consistent with the surface bands. And to our great surprise, we observed at some points along the horizontal direction a Dirac-like cone structure, and slightly off the zone boundary, actually double Dirac structure. So we studied those in more details. We first verified that these are indeed Dirac points. There's no, they're not gap. There's a peak of intensity exactly at the location of Dirac points. So there's no gap present. The same is true for this double Dirac structure here. And what was most surprising, actually, this double Dirac structure, they not really Dirac cones, they actually linear planes of two bands intersecting each other that are mostly linear, and they intersect each other without forming a gap. So if you look at this point near off of the brilliant zone, you can see just a single Dirac cone, and this is actually actual Dirac cone. You can see separation of the bands as you move away from the Dirac point. Then this band splits into two as we travel towards the X point. And now here detailed cuts here reveal that this gap, which is present, which is remnant from the going away from the Dirac point, then becomes gapless. So you have a linear dispersion crossing each other at two different points, and then remain gapless for actually quite extensive distance momentum space, and then become gaps again on the other side. And the graphical representation of this would be two Dirac cones on either side of the brilliant zone. And through the brilliant zone, there is a set of points at which the dispersion is effectively at two intersecting planes. And we call this construct Dirac arc nodes. There is a possibility that perhaps the spin orbit splitting is causing this effect. But to this date, this is not quite well understood, and I hope somebody eventually is going to figure it out. So with this, I would like to thank you for your attention, and I welcome any questions you might have.
Thank you, Dr. Professor Kaminsky, for a wonderful talk and a very nice overview. Now the session is open to questions, and then first I will invite the offline participants. If they have any question, please go ahead.
Yeah, this is Seti. I have Professor Kaminsky. Thanks a lot for the nice talk. I have a couple of quick questions. One question from your this rhodium bismuth tool. I hope if I remember correctly.
Mm-hmm.
Yeah, there you mentioned somewhere one Hall singularity. Yeah, right. So somewhere you mentioned one Hall singularity, but the bands are a bit far away from the Fermi level, isn't it? I think slide number 16.
Yes, it's about 80 MeV.
80 MeV. So still can we consider this as a one Hall singularity, something like that?
Yeah, so in this, yeah, you're absolutely right. In this material by itself, we don't expect to observe anything in particular. But what we're hoping to do is maybe dope it or do a chemical substitution.
Exactly.
Where we shift the chemical potential, closer to the one of a singularity point, and then expect sort of some more exotic effects to appear.
So, I mean, you have done several experiments getting one Hall singularity by changing temperature. Did you try to get this here by changing temperature, something like that?
Right. So in this material, we don't observe significant movement of the EF with the temperature.
Okay.
Yeah, this effect is much stronger in tungsten ditelluride, where you can move it by about 50 MeV. But in this material, unfortunately, because there's many, there's number of bands present, this effect is very, very weak.
Okay. And my other question is the last part, that platinum tinfoil. So the bulk band structure calculations do not show any Dirac state there. Yeah. For example, the KZ, the middle panels too, like EDM, middle EDM.
Right.
Yeah. So there, your KZ EDM, yeah, as you say, I mean, you said it's not understood well. So you think it's the bulk therefore that what you see there?
No, so along the horizontal direction, the structures we see, I think that we are fairly sure these are the surface states.
Surface states, okay. Thanks. Yeah, that was my question. Thanks a lot.
Typically, the band, if it's a bulk band, you have a projection along KZ direction. If you look at this top part here, there'll be very strong intensity in between the bands. The bands will be very barely visible. Exactly. If you see something as sharp as here, this is definitely a surface state.
And have you done surface state calculations? I mean,
so the surface state calculations here, I don't know if I have. I probably don't have on the hand. Yeah, I don't have on the hand the cuts through this.
Okay.
But they're not quite what we see in their experiment.
Okay. Okay.
Yeah, I have one question. Yeah, so in this PTSN4, you showed that this Dirac cone it splits. So how do we understand it? Because it is a central symmetric system and there is no magnetism involved. So how do you explain?
Right.
This?
So okay, I perhaps use a slightly wrong terminology that splits. I just describing what the data looks like. But indeed, in fact, this is just there are just two cone-like looking features in some part of the brilliant zone. So it's not a splitting as a sort of function of temperature or anything else. It's just as you make cuts to a brilliant zone, it looks like you have a Dirac cone. Then you see a gap here because if you cut the cone through the side of it, the top and the bottom will be separated by some energy. It's not really an energy gap, it's just separation of two bands. But then if you go further, then sort of this what used to be here, this is just evolution of the band structure as a function of momentum. It's not sort of a splitting in terms of finding the magnetic field or inversion break, symmetric breaking.
Okay, any other question from the offline participants? Okay, then we can start the online. And Gaurav Shukla, I think you have raised your hand, so please go ahead with your question.
Yes, sir. Thanks for very informative talk, sir. So one of my simple question is in this. So in one slide, you have told the electron and hole pocket in the surface state calculation. So how, sir, we identify, okay, this is the hole pocket and this is the electron pocket. So yes, so
The calculation?
yes.
Oh, yeah, so right. So if you can tell by the dispersion, right? So if you just look at the Fermi surface, it's difficult because it's just a round object. But we can have cuts like here, and then you can tell, this is this is, for example, the hole band because it goes like this. So this is near the top of the band, and this one's electron band because it's the bottom of the partially occupied band. So by performing the cuts in momentum space, we can tell the two apart.
Okay, sir. So this is why the dispersion of the bands, how they disperse in concave light or convex light.
Yes. For example, this pocket here, this is just top of the band. So most of the band is occupied, and you have a small top of the band that's unoccupied that sort of sticks out at EF here. That forms a whole pocket. The pocket here is sort of the bottom of the band, where only bottom of the band is occupied by electrons, and we call this an electron pocket.
Okay. You are satisfied?
Yes.
Satyabrat Patnaik, she can.
Yes, basically the question is on MnBi to T4. Then you mentioned that it has kind of similar properties as MnBi6 T10. So both in terms of the magnetic aspects, I mean, how does it compare to MnBi to T4? I mean, both RPS and the magnetization measurements.
Right. So in the magnetization, actually, the critical temperatures are very close. They're about 20 something Kelvin, where you have an anti-ferromagnetic order in those. We don't have detailed data about the magnetic structure, but we can assume maybe that because it's the same type of manganese layer, that the magnetic order is probably the same. And it seems that, if you look at this very early data from the Moscow group, this sort of gap opening here that is sort of broad and slow. And if you look at the evolution of intensity at the gap value, it's not clear that there's a clear break between, below and above the critical temperature. And this is actually kind of consistent with what we see, is that this gap does not exactly close at the magnetic transition temperature. It actually closes substantially higher above. So it seems that the data from 1.610 and 1.24 are actually quite similar.
Okay, thank you.
Okay, Professor Collaborators.
Hello, good morning. Very interesting talk. So I have two questions. One is that, for example, this WT2, where you have shown this extremely high magneto resistance. So is there any understanding apart from this electron hole compensation that people have been talking about? I mean, what is the origin or underlying physics of that?
I'm sad to say that we didn't make much of a progress with it.
I see. Okay. So, but I mean, yeah.
You're right. The only sort of the common theory is the carrier compensation. It's sort of hard to argue for and against. We do see that if you change temperature in tungsten ditelluride, there is a Lipschitz transition, so the Fermi surface is actually changing shape. So it's possible, and actually, indeed, at low temperatures where you see this large magneto resistance,
Yes, yeah.
both Fermi surfaces look roughly of the same size. So
Yeah.
we're consistent with this theory, but we can also sort of say this is definitely true.
Okay. The other point which I wanted to know from the experimental point of view, I mean, is it from ARPES, do you find any signature to identify these Weil nodes and Dirac nodes? I mean,
right. So the only evidence we have for the tungsten telluride is the presence of Fermi arcs.
Okay.
Because they note this is something that is, if you look at the calculation of the Fermi surface here, just disconnected hole pockets here and electron pockets here and hole pockets here. There's nothing connecting. The surface state calculation does not reveal anything. The only explanation for those things here is that these are Fermi arcs, and these are with the Fermi arcs in a Weyl metal that has to be Weyl points here.
I see. So I mean, once you see the Fermi arcs, of course, then that's a good signature.
Right.
Okay. Okay. Thank you.
You're welcome.
Okay, any other question from anyone? Okay, I just have one small question. This Fermi arc is really a surface state, or it's a bulk state projected on surface? So how it is exactly?
It's a surface state. So the definition of the Fermi arc in topological materials, it has to be surface state.
Okay,
and
so basically the wave function of that surface state vanishes in the bulk. So it should be like this.
It merges with the bulk bands at the surface. Yes.
Okay.
And experimentally, we have two ways of saying it. We can either look at the sharpness. So if you look here, these are very, compared to bulk bands, which are huge abroad, these are extremely sharp. And we can also verify with the photon edge dependence that there's no KC dispersion for those.
Okay. And about the splitting of the Dirac cone and Dirac cone without any above the magnetic transition temperature, do you have any possible candidates to explain the origin, or is still unclear?
So could you last part? I think something.
No, there was a splitting of exactly this figure. The splitting of Dirac cone, split Dirac point above the magnetic transition temperature.
Right.
So, do you have any candidates for the origin for such a phenomena, or is it still unclear?
You know, the hand waving explanation we have that this is some very strong magnetic fluctuations, right? That sort of naturally occurs. But again, I mean, 150 Kelvin for the 24 Kelvin magnetic transition seems kind of high.
Okay.
So yeah, this is something we don't quite understand.
Okay. So yeah, I think Amit has a question. Amit Agarwal. So can you quickly just give as a wind up the things? Quick question, yeah.
You have to unmute. Amit, you have to unmute.
So it's sort of a speculative question. So how do we see, let's say, this higher order topological states or edge modes in ARPES experiments?
Well, in a number of ways. It depends on the type of edge state. So if you remember on the beginning, in the bismuth iodide, this was done by using a very small beam and sort of looking at the cracked edge of the sample.
I see.
You know, technically, the Fermi arcs are the edge states, because for the three-dimensional material, looking with ARPES on any planes where those are present, these technically will be edge states.
Yeah. Okay.
Okay, so it was a very interesting talk and very nice overview of the field, which it is going to be very interesting for most of the people who are in this conference. So I'm glad to have such a nice talk being delivered. So let's thank the speaker for his wonderful presentation. And let's move on to the next talk. Is Dr. Amit Agarwal from IIT Kanpur. And the title of that talk would be, just hold 1 minute. Yeah, the title is The Berry Curvature Dipole Senses Topological Transition in Moir Superlatives. I guess it's a theoretical paper. So I hand over to Dr. Amit Agarwal.
Yeah, thanks a lot. So I'll just share my slides and then. Okay. So let me just share. So my slides must be visible now.
Yes,
right?
yes, yes.
Okay, so I'm going to go in the play mode. Okay. Okay, so let me start by thanking the organizers for organizing this conference, and secondly for giving me an opportunity to present this very nice work. Actually, okay, so this is a work which is a combination of experiment and theory. I did mostly theoretical part of this calculation, and the experiments were done in Mandar's lab in TIFR. Okay, and we also had theoretical support from Professor Umesh Wagmare's group at JNCSR. Okay. So I'm going to talk primarily about band geometric properties, and in particular, there's this one band geometric property which is the Berry curvature, and it manifests in second order or nonlinear Hall effects by this quantity which is called Berry curvature dipole. Yesterday, we had a very nice talk on Berry curvature dipole related physics by Avdesh Narayan. So that makes my job a bit easier. And we will try to connect this Berry curvature dipole, number one, measurement in Moire superlattices, and number two, connected to a topological phase transition, basically observed experimentally and supported by theoretical calculations. Okay. So let's go ahead. Okay. So a very quick introduction to geometry of the block bands. So I think Avdesh gave an introduction to the Berry curvature already yesterday, starting from this adiabatic theorem and evolution of the wave function, etc. Here's an alternative way of looking at the same thing. So you can try to think of quantum geometric quantities in terms of distance between nearby states, let's say. So I take a state, so if I'm in the Brillouin zone, then psi k plus dk minus psi k. So that's roughly like the difference of two nearby states. And I just measure the distance between these states, basically. Okay. And if I do that, okay. So you guys are seeing my second screen, right? Just confirming.
No.
No, we're seeing just the first.
Okay. So let me then, okay, so some issue. Okay, so let me just switch to PDF version of this. Okay, so I'll just stop sharing and then let's. Okay, so I guess this PDF is available, right? And let's just quickly check that slides are moving, right? So you guys see the first slide, right? Yeah. Okay. So now we can go ahead. Okay. Yeah. So let me start again from quantum geometric properties of the electronic wave function. So in addition to what Avdesh did yesterday, starting from the adiabatic theorem and introducing Berry curvature, an alternate way to think about this geometric quantities, distance between nearby states. So if I write this distance between nearby states, I get this quantity, which is in terms of derivatives of the wave function. And this quantity in particular, you can define as what is called a geometric tensor, which has two components, symmetric part and the anti-symmetric part. And the symmetric part, you can think in terms of quantum metric, and the anti-symmetric part, you can think in terms of the Berry curvature. Okay. And these are the most important quantities if you want to describe anything related to let's say the topology of the system, or if so almost all topological indices for all the materials that we discussed in the previous talk, etc. Everything, all topological indices can, for example, be written in terms of this Berry curvature integrals, okay? Integrals over the Brillouin zone. These are also intricately connected to the surface states, etc. So all the states that we talked about. more importantly, and this will be the focus of my talk, so these geometrical quantities also give rise to new transport and optical phenomena. Okay? In particular, so some prominent examples are anomalous Hall effect or Valley Hall effect in graphene-like systems, etc. And more recently, there's been a lot of interest in nonlinear transport properties, particularly the nonlinear Hall effect, which will be the focus of this talk, actually. Okay? So let's move to Berry curvature dipole. So I'm going to talk about nonlinear anomalous Hall effect, which is the second order. In terms of, if I apply a fixed current, I measure a voltage. If the voltage is proportional to I square, then that is a nonlinear anomalous Hall effect I will talk about. So second order nonlinear anomalous Hall effect. And Hall, because I apply a electric field or let's say current in the x direction, I'll measure the voltage along the y direction. And this became came to prominence because of this particular paper by Inti Soderman and Liang Fu in 2015. Which was titled as Quantum Nonlinear Hall Effect Induced by Berry Curvature Dipole in Time Reversal Symmetric System. And the idea is that, in time reversal symmetric systems, you expect in the absence of magnetic field, there'll be no anomalous Hall effect. Okay? So then the idea is, what is the lowest order Hall signal that you can measure in such materials? And this is the first nonlinear Hall signal, second order nonlinear Hall signal that you can measure. Okay? So this is the Hall effect, lowest order Hall effect, which you can measure in time reversal symmetric systems in the absence of a magnetic field. So that is important. Okay. This is induced by this quantity, which is called Berry curvature dipole. So if you look at the expression here below, then this integral over the Brillouin zone, if this is called this Berry curvature dipole. So omega is the Berry curvature, which I defined in the previous slide. And if you take the derivative of this guy along some direction in the, let's say, Brillouin zone, so dou B is dou by dou KB actually, okay? And you integrate that derivative by convoluting it with the Fermi function. So that quantity is called this Berry curvature dipole. Okay? And of course, since this depends on the Berry curvature, I need to break either inversion symmetry or time reversal symmetry. So if you're talking about time reversal symmetric systems, then I need to break the inversion symmetry. That is number one. And inversion symmetry is not solely sufficient. We also need some asymmetry of the band structure. Otherwise, this integral generally vanishes, actually. Okay? So we need these two essential criteria: inversion symmetry breaking and asymmetry of the band structure. That's one. And so this was, second order nonlinear Hall effect introduced by this band geometric quantity, actually. Okay? But this is not the only effect which can introduce nonlinear second order nonlinear Hall effect. There are a lot of extrinsic scattering dependent, anomalous scattering dependent effects which can also introduce this anomalous nonlinear anomalous Hall effect particularly. Okay? So in particular, there are specific contributions which go by the name of side jump scattering, let's say number one, or skew scattering. Okay? So these are like so these give you additional nonlinear Hall contributions basically. And with the advent of experimental systems trying to probe this nonlinear anomalous Hall effect, I mean there are these two papers did the complete theoretical analysis of these, etc. In particular, this paper tabulated all the ways in which impurity can contribute to these contributions, and this will become important when we try to experimentally probe this signals, because separating these extrinsic signals from the intrinsic BCD dependent signal will become important actually. Okay. So here, for example, is a plots for simple, very simple theoretical model, massive Dirac system. So, for example, the Berry curvature dipole dependent term is this blue line, and the side jump and the skew scattering contributions can be of the same order basically. Okay, such that if you look at the total, which is this black line, then that can be sort of reduced, etc. And this black line is what we will measure in the experiments, and we need a way to convolute and bring out this blue line, let's say, because this blue line is related to band geometric quantities, and it will sense what I'm going to describe next is this valley churn number in these systems. Okay, and all of these scattering terms also involve this Berry curvature effect. So if you solve for the full scattering problem, including Berry curvature in the equation of motion, etc., then you will get all of this important contribution. And of course, all of this physics is not entirely new. This framework has been explored in the context of anomalous Hall effect long back, let's say. Okay, so 2010, 12, 14, and so on and so forth. Okay? Okay. But that's the important idea. So we are looking for nonlinear anomalous Hall signal. It is composed of some BCD contribution plus some scattering dependent contribution, and we'll have to work to separate out these two actually. Okay? And here's the way to separate out. So experimentally, we never measure the conductivity directly. So experimental measurements, we generally apply a fixed current, let's say, and we do generally AC measurements so that we can use lock-in amplifiers to separate out the signals. So we apply a fixed current at a given frequency omega, and we will measure the voltages, let's say. Okay, so if you want to measure the linear response, then we'll measure the voltage at omega. If you want the nonlinear response, then we'll measure the voltage as 2 omega, 3 omega, so on and so forth. Okay, we will limit ourselves to second order nonlinear, so we 2 omega. Okay, so the measured, so if you try to convert, what is the conductivity and write it in terms of resistivities or the voltages measured, etc., then you can show that the measured nonlinear voltage, which you measure at frequency 2 omega, and this longitudinal voltage at frequency omega, they are related by this expression basically. Okay? So the nonlinear Hall voltage along y divided by the nonlinear response Dude voltage mod square is related to this nonlinear Hall conductivity divided by the Dude conductivity. Okay? And note that this is very generic, and this still includes both the BCD and the extrinsic contributions, etc. Okay? But now we can go ahead and do more careful analysis, etc. And if you do analysis including all of those terms that we very quickly looked in the previous slide, basically. Okay, so all of these contributions, if you include and do a careful scaling analysis, etc., then we can show after some algebra that this ratio, so the nonlinear Hall voltage divided by the longitudinal linear response Dude voltage mod square can be expressed as A times sigma xx Dude conductivity whole square plus B. Okay, and this gives us a lot of insights, this calculation, etc., in a sense that if you do, you find a way to convolute the BCD signal from the extrinsic signals, etc. And the main output of all of this analysis is that the intercept for this curve is only dependent on the BCD. So if I measure the intercept and I then I can extract the BCD signal, and the slope of this curve basically is still a combination of BCD plus all of these extrinsic effects, etc., which are difficult to separate. So we will not worry about the slope that much. We will just focus on the intercept actually. So the intercept of the scaled curve with the square of the Dude conductivity will give rise to BCD. So that's the major idea. Okay, so now we want to plot this ratio V nonlinear Hall signal divided by V Dude longitudinal conductivity dependent voltage mod square, etc., as a function of conductivity, right? So how do you vary conductivity in an experiment? Okay, so conductivity you can vary by either varying temperature or by varying external electric fields, and these two will play an important role basically. Okay? So there are a lot of works earlier which do experiments by varying the temperature, but if you vary the temperature, then it has an additional effect that it also modifies all these extrinsic contributions, etc. Okay, so if you do experiments like that, then you cannot be 100% sure of the correct scaling behavior with conductivity, etc. Because the sigma xx square itself is changing, number one. And the coefficients A and B also may change with temperature, etc. Okay. Okay. Now in this 2D kind of systems which can form this dual gated devices, you get this external parameter which you can apply and tune the band structure or electronic properties of the system, which is the external electric field. So external electric field I apply, I change the band structure of the system. We'll see more details a bit later. But once I tune this, I can now, so with the tuned band structure, by changing the vertical electric field, I can map out the conductivity and I can make this plot at the same temperature basically. So I'm not introducing any temperature dependent phononic effects, etc., in these coefficients A, B, etc., and I can still do the same measurement. So this is what we will do in what follows, and separate out the BCD dependent contribution, number one. So this will be the first measurement of, let's say, BCD, which we will show that it has a relatively large value in graphene based Moire systems, number one. And then we next show that this will be sensitive. It will change sign when we tune the electric field to take it across a phase transition, basically. So these are the two things I want to establish by the end of this.
Can I interrupt a little bit? I hope the title of the slide currently is experimental measurement of nonlinear Hall effect, or
Correct.
is it okay? It's still there. Okay. Oh,
Yeah, correct. Yeah.
Okay, fine.
Thanks. Okay. So here are some excitement in this field, etc. So nonlinear anomalous Hall effect. So 2018 particularly was sort of quite event foot for this nonlinear Hall effect. This theory paper demonstrating this in WT2, probably because there are a lot of experiments. At least these two experiments were in progress, etc. And both showed the Berry curvature dipole, existence of Berry curvature dipole, etc. Measured via this nonlinear Hall measurement. And here's an example in WT2 twisted, basically. So I think probably the first example in twisted Moire system where you experimentally measure this quantity, nonlinear anomalous Hall effect. Okay. So the measurement is here. So these are mostly theory plots of the band structure, Berry curvature dipole, etc., and the corresponding integrals of the Berry curvature and the Berry curvature dipole density, actually. But this is one of the papers which showed the existence of this Berry curvature dipole in Moire systems, actually. Okay. So let's come back to now Moire systems, which is our experimental test bed. And why are these systems exciting? Quick preview. So primarily exciting because of tunable electronic properties. You can change the vertical electric field, let's say. You can change the band structure. Topology, I'll show example. You can, since a lot of these materials will come with flat bands, you can change correlation effects, etc. So twist angle, vertical electric field, and doping, which you can control in dual gated devices, can serve as knobs for tuning external electronic or topological properties. These have topological flat bands and Moire bands, and each of these bands can have a valley churn number. So the topological index for these materials, etc. And these are playground for band geometric effects. So Berry curvature, BCD, etc., which is what I'm going to talk about in the rest of the talk. Flat bands give rise to Van-Hoff singularities in the DOS, and that makes it a playground for strong correlation effects. In fact, the whole interest in this field recently, after the initial papers started from demonstration of superconductivity in twisted bilayer graphene, etc. So they can show superconductivity, magnetism, and ferroelectricity. Okay, so these and combination of, let's say, band geometric quantities and superconductivity or magnetism that can give rise to more exciting avenues for exploring new physics, etc. So there's some popular papers in this. So this is very, very sparse literature, very few. So this particular paper by Pistreiser and Alan McDonald gives the theory for forming the band structure of these kind of things, starting from a low energy effective Hamiltonian. And this is the approach which is generally adopted for studying these materials, etc. Although there are other approaches also. Okay, but this unconventional superconductivity paper, I think this is the paper which started this whole recent excitement in all of this field. And yesterday we had a very nice talk by Professor Burnwick trying to find the reason or classify all materials basically which will have this kind of flat bands, etc. Okay, and these are the outcome of the talk was all of these bands are essentially tied to topology in some way or the other, and they will generally have this nice band geometric properties basically. Okay. So that's a very general physics. This is one specific example. Okay. So very quickly, so this is, I'll talk about twisted double bilayer graphene. So there's a bilayer graphene, on top of it bilayer graphene, and they are twisted upward basically. Okay. So by some very small angle, we'll talk of typically 1 degree rotations. Okay. And by virtue of this small rotation, the Brillouin zone basically so the lattice becomes very large effectively, and you need to be very, very careful in modeling this lattice actually. Okay? So here's an example of how you will sort of model. So displaced lattice. So let's say these are the two atoms which they are supposed to be aligned with each other. They are displaced top bottom slightly, and if you just take one pair of this and try to make a Hamiltonian for just this red atoms, which is coupled to, let's say, 3 nearest atoms like this actually, then you get essentially a 16 cross 16 Hamiltonian just for one point actually. And all of these blue points to which it is coupled to, they are also coupled to nearest 3, etc. And you need to keep doing this till you get sufficiently good band structure, etc. Okay. So typically, I mean, even to get a reasonably close band structure, which has, let's say, flat bands, etc., you need to go to some lattices or, let's say, matrices, which will be like 600, 700, 800 cross 700, so on. Okay. Okay. So with that, let's go ahead. So we take this Hamiltonian, do this careful construction, and here's the demonstration of band structure and the tunability of band structure, etc., how it is sensitive with respect to twist angle and the vertical electric field that you can apply. Okay. So these are theoretical plots, etc. So just in the band structure, so you go from, let's say, theta is equal to 1.05 degree to theta is equal to 1.33 degree here. Just in the band structure, the difference is not that visible. But if you just plot the difference between ECB minus EVB, then you see this stark contrast basically, right? So your bandwidth goes from 40, let's say, to 60, and so on and so forth. Okay, so the structure of the bands completely changes, etc. Okay. And similarly, if you apply a vertical electric field, let's say, between the same theta 1.05 to theta 1.05, but you apply a 12 MeV vertical electric field, well within experimental achievable range, then also you make this drastic changes in the band structure. Okay. So the takeaway from this slide is, first conduction and first valence band. So these two bands basically, which are, within 10 MeV of the Fermi energy, are the flat bands basically. And they are accompanied by these higher bands, which are dispersing, and they are typically called these Moire bands in the literature. Okay. So these, of course, these flat bands are accompanied by Van Hoff singularities, etc. Okay. So even this Moire dispersing band that we are talking about, they are like 20, 30 MeV in bandwidth, and they also have Van Hoff singularities actually. So this is something which we miss sometimes, but yeah, that also you should keep in mind, that this Moire bands can also give rise to interesting physics basically. Okay. And each of these bands generally has a finite Berry curvature. And so the band structure I'm showing you for a K and a K prime valley. So when you do low energy models, you need to construct separately the bands for the K and the K prime valley. The full band structure is, of course, the material has sum of both this set of bands, etc. So the full band structure is sum of these bands. So you need to sum over these valleys, etc. So each of these valleys or each of these bands have a Chern number. And then I need to define, since it is a time reversal symmetric system, so the total Chern number, when I sum over the values, has to vanish. I'm forced to have that because of time reversal symmetry, but we can still define a valley Chern number, which is the difference between the Chern number of this valley and that valley. Okay? And that forms the topological index for this set of materials, basically. So Chern number you define by doing a Brillouin zone integration of the Berry curvature for a given band, basically. So it is band specific. And valley Chern number you define, you calculate for one valley, you calculate for other valley, and you take the difference basically divided by 2 and the mod of the difference. So that's the valley Chern number. And here I show the topological phase transition. So this is a phase diagram in the space of, let's say, the vertical electric field and strain. So you can vary strain and you can vary the vertical electric field, and you can have different valley Chern phases. And this is just for the, let's say, first conduction band or the flat conduction band, and this for the flat valence band, etc. You can go from Chern numbers of, let's say, 0 to 3 in this particular figure. Okay. And similarly for the valence band, you can go from Chern number of 0 to -3 and so on and so forth. And each of these topological phase transitions, so suppose I traverse a line, I am sitting at 0.1% strain, and I traverse this line by varying the vertical electric field, I will go from one phase to the other, etc. And we can show by very close analysis that each of this phase transition is accompanied by a band touching point, basically, as you would expect. Anytime a Chern number changes, there's a band closing and band opening, and basically the band inversion changes sign, basically. Okay. So all topological transitions are accompanied by band touching points, and band touching points should not be confused with metal insulator transition, because I can have metal insulator transition even without bands not touching each other, basically. Okay? So I can have a DOS overlapping, so I can have metal insulator transition. And this is like, at the same K point, the two bands have to actually exactly touch each other, etc. Okay. So that the topological phase transitions we saw. Now, let me just show the Berry curvature. How does it look like in the Brillouin zone? So this is for strained, 0.0%, 0.1% strain. So that's how the Berry curvature will look like. First conduction band, first valence band, etc. And given this Berry curvature, we can calculate the Berry curvature dipole using this integral of the Berry curvature. So derivative of the Berry curvature over the Fermi function, or alternately, it can be written in this particular form by transferring the derivative to the Fermi function. Okay. That's an alternate way of writing this, which shows that is a Fermi surface property actually. Okay. Okay. To have this finite in these systems, so these are graphene-based systems, even without strain, even the twisted bilayer graphene or twisted double layer graphene, both of them have this C3 symmetry basically. Okay. So the rotational threefold rotational symmetry actually. And if you have threefold rotational symmetry in the system, they will so this Berry curvature dipole will vanish. So that I explain in the next slide. And this strain induced breaking of the C3 symmetry is crucial for generating a finite Berry curvature dipole in this systems basically. Okay. So here's some plots as I vary delta from 11 to 15 to 25 MeV. How do the bands move, let's say? And here's the plot of the Berry curvature dipole. Okay. So these are theoretical calculations. We go to the experiments in the next slide basically. Okay. So this is the last theory slide I have. And next I will have only experiments. So as I was arguing, strain breaks C3 symmetry in this twisted double bilayer graphene, and that generates the this thing. Okay. And the idea is the following basically. Okay. So let's say I have this perfectly hexagonal Brillouin zone. I take this C3 symmetry related diagram. If I calculate the omega z basically, that's the only finite Berry curvature component I can have in 2D systems, then they exactly overlap each other. Okay. For each of these three paths basically. So I'm just the path length is just going from the gamma point to this or here to here and so. So if this is true, then the derivative of this omega along these paths will also be identical basically. Okay. And if they are identical and you use this triangle rule of summing over these three vectors, then they have to vanish. Okay. But strain somehow modifies this Brillouin zone, etc., and these directions become non-identical. Okay. And with strain, you see that this Berry curvature along these three C3 symmetric paths are slightly different, and their derivatives now need not add up to 0 if I sum over the full Brillouin zone. So that's the idea. So C3 symmetry breaking because of strain is important. And more important is, in any experimental system, I will always have strain basically. So you can image these systems and you find that they never form perfect hexagons or perfect triangles, let's say, so there are always some distortion, etc. So all of this point to strain in the system. Okay. So for the strained system, here's how the Berry curvature in the bands look like for first two conduction band, let's say, and here's what the Berry curvature dipole looks like. And you can clearly see that, if I have zero strain, then even though the bands are very close to each other, etc., the Berry curvature dipole is identically 0. Okay. But if you put in the finite strain in the system, then you start having this finite Berry curvature dipole in the system. So that's the whole message out of this slide. Okay. So next, let's experiments. Okay. So first, let's establish the observation of nonlinear Hall signal in strained bilayer graphene. Strained twisted bilayer graphene. So here's the experimental setup, the schematic, let's say. So you have this twisted double bilayer graphene. So AB stacked bilayer graphene, another AB stacked bilayer graphene, and they are rotated in the center with respect to each other by this angle close to 1 degree actually. So for this set of plots, this is specifically 1.1 degrees. So you can apply a fixed current between 1 and 4 terminals. And you can do a measurement of longitudinal Dude voltage, let's say, along 6 and 5 terminals. And you can measure this V2 omega signal across the 6 and 2 terminals. So that's roughly the measurement setup. And if you do this, you can actually show that, this V2 omega, so the orange lines, basically, these are experimental measurements. You find this finite BCD by tuning either the vertical electric field, or you can also tune the filling factor basically. So this is a tuning of the filling factor actually. Okay. So this for zero electric field, and this for finite electric field value basically. Okay. So two different sets. So this just establishes that there's nonlinear second order Hall voltage in the systems, which in turn establishes that there's very curvature dipole and extrinsic nonlinear effects, coming from side jumps, Q scattering calculations, etc. We still need to work on this to disentangle basically. And this 2D materials have this added advantage that you can make dual gated devices such that you can have control over the vertical electric field and the doping independently basically. So that's the tunability or tuning knobs for this system. Okay, so here's the observation of nonlinear Hall effect. More details actually. So the first panel shows just the Dude voltage, just mapping out the density and electric field regime, where it is metallic, where it is insulating, etc. So this is 0 filling, and near the 4 filling, which is almost touches the Moire band. Let's say you have this structure basically. Okay, so we have this Dude voltage, which you can also map to the Dude resistance here basically. So that's the color scale for the resistance. Okay. So the x-axis is nu and the y-axis is this vertical electric field, and the top x-axis is the density. So nu converted to the charge density. Okay, so that's Dude measurement. So that is okay. But this is the nonlinear Hall signal that we have been talking about in this whole talk. So here's the map of the nonlinear Hall signal in the space of vertical electric field and the doping basically. Okay. And now that you know that where are they finite, so they are finite near the band edges as we expect, because the Berry curvature hotspots tend to be near the band edges, or at least wherever the bands are sort of flattish and have more DOS weight, etc. Okay. And so we can do experiments by sitting here or sitting here, or sitting at any of these 4 corners. We will choose particularly to explore along this charge neutrality, let's say, line. So 0 filling line basically. So here's the vertical cut of this. This is new. So horizontal cut of this one of these plots, which specifically shows this nonlinear Hall voltage basically. Okay. And just to establish that this is indeed scales with Vxx Dude longitudinal voltage square. This plot shows that basically for 2 sets of parameters for filling and the density number 1. And just to check that this nonlinear Hall voltage is indeed coming from the sample and not something specific to the contacts actually, you can actually switch the current contacts and the voltage contacts, etc. Just to show that the polarity actually reverses. So this just establishes that this is number 1 second order nonlinear Hall, and second that it is not coming from this contacts or some other spurious effects actually. Okay. So this establishes nonlinear Hall effect. We still have to work a bit more to extract the BCD, Berry curvature dipole, from the y-intercept of this curve, the scaled curves with the sigma xx square, and we still need to connect it to topological phase transition. Okay, so that's my last job basically. So one more theory slide for topological phase transition and its relation to BCD, let's say. Okay. So here's a plot for the BCD.
Wind up 5 minutes. 5 minutes.
Yeah, I'll be done. So this is a plot of BCD as a function of the vertical electric field, and let's say the energy, which you can think roughly in terms of chemical potential, just that each of these data point is for a different band structure actually. Okay, so to make it homogeneous, we measure all of these energies from the top of the valence band near the charge neutrality point basically. Okay, so that's the energy basically. So it's not precisely chemical potential, but roughly it should be thought of as chemical potential. Okay, so the point is here. So you, for example, vary the delta. So for this plot, we have specifically picked out one particular topological phase transition. So you sit near some energy 40, let's say, and you vary delta. So you will have this kind of a structure in the color plot of BCD basically. And this is what we will pick up in the experiment. Okay? So we cannot do this mapping in the experiment, but what we will do is we will just scan one line along this delta, etc., and that is what we can measure. Okay. So here's the theory of how does the band structure change across this phase transition. So this is phase transition where Z2, the valley churn number, was 0, or lower delta, the valley churn number is 2 basically. Okay. So for the same phase transition, I have this band structure. Let's say delta is equal to 25 MeV. So the band transition is around 34, let's say MeV roughly. So 24, 30, and across the phase transition 38, 43, etc. So that's the color coding shows the Berry curvature, and that's how the bands evolve. And you will see the complete switching of the colors, etc., as soon as you go across the phase transition, which is expected because the Chern number itself is like the integral of the Berry curvature. So if the Chern number is changing, then the dominantly the Berry curvature magnitude must have changed across the bands. But it still doesn't say that the Berry curvature dipole should change sign and so on. So, but that's the idea. If you go across that, this is the connection between the dipole and the phase transition. Okay, now let's go to the experiment once. Okay, so recall that we had established this relation basically, right? So Hall voltage, when scaled by the longitudinal Dude conductivity linear response square, should scale with A times sigma xx square plus B, where B, the intercept, gives you the BCD actually. Okay? So here's the scaling, Vxy 2 omega divided by Vx linear response, so omega whole square basically measured. So this black line, okay, and you clearly see the change in behavior. So there's something happening here, we do not know, but you can actually probe this further by measuring sigma xx square, just the Dude conductivity, and you see that something is happening here also. So this definitely is sort of a metal insulator transition, number one. We still do not know whether it is a topological transition or so on and so forth. Okay. So now you measure the you do the plot of the scaling curve. So Vxy divided by Vxx square in terms of sigma x square. And you start seeing that you have this region 1 where you are in this phase, and region 2 where you are in this phase, etc. And these two lines are sort of, give you completely different intercepts when you cross this point of minus 0.23 volts per nanometer in terms of electric field, etc. And this jump in the intercept actually is connected to the topological phase transition. Okay? And you can use the intercept, this green line and this blue line, so this intercept, to extract the Berry curvature dipole actually. Okay? And that looks like this positive on one side and negative on the other side basically. And this is what I was just trying to argue, that if you have a topological phase transition, you will see the effect in the BCD, etc. So here's the plot of the measured BCD before and after transition. So whatever was the peak basically becomes the dip. So the green arrow here becomes the green dip here basically, and the violet, let's say peak here, becomes the violet dip here. So this is the sign flip in the BCD, which if you actually make a more careful plot will result in this butterfly plot.
Can we wind up a little bit?
We're done almost basically.
Yeah.
Okay. Thanks. So that's number one, nonlinear Hall. Intercept gives you BCD, and sign change of the BCD gives you the phase transition basically. This Chern number change actually. Okay. So that's the complete story. BCD in Moire superlattices senses topological phase transitions. Okay, so just to establish that this is not some spurious effect, etc. Mandar's group did a lot of very careful experiments, and this is a lot of checks for different filling factors which show identical physics. You can take this to the valence band doping. So and check. So that also we did. An additional check is this, so you can make another sort of devices. It may be specific to this devices. So so that was for 1.1 degree. So these are for two different devices. So 1.09 degree and 1.26 degrees. You find the same physics basically. Okay.
Wind up
and that, yeah, I would like to basically conclude. And here's the summary.
Okay, so let's thank the speaker for. So the session is open to question. Offline participants, please go ahead with your question first, and then we'll go to online ones.
Okay, Amit, this is Siti. Thanks for the nice talk. I have one basic question, that these BCDs are available, are present only in bilayer systems, or in bulk also we can find them?
No, in bulk also they are there. So while Semimetals, you can find examples basically, etc.
Yeah. So in bulk, if that is the case, so usually they appear in wire systems, right? Not in Dirac.
So you have to be careful here actually. So they can also appear in Dirac systems, etc. Right?
if they appear in Dirac, then how do you get these dipoles?
So you need to break inversion symmetry or time reversal symmetry, basically.
You end up in wild systems.
Either of them, basically, yeah.
So now, so what would be the difference between time reversal symmetry breaking BCD and then inversion symmetry breaking BCD?
Okay, so time reversal symmetry breaking, say number one thing is you will get anomalous Hall effect itself, basically. Okay, so if there is some phase transition, then there should be signal in anomalous Hall effect itself, basically.
Okay, you mean to say there is no difference between those two?
No. So, in what sense, basically? Let me, make your question more sharp.
So, okay. So, for example, so here I'm considering this BCD, like what a very curvature dipole.
Yeah.
2 wild points are giving me 1 BCD. Is it like that? Can I?
No. Okay. So you are thinking of this wild nodes as basically, yeah. Okay, I understand. So what is the question then?
So now, so if that is the case, then for inversion symmetry, I should see the least number of BCDs would be 2, and for time reversal symmetry, there should be 1 BCD.
Why 1? So these are not necessarily quantized, basically. Okay.
Least number. So inversion symmetry least number would be 2.
Okay, so we are talking. See,
least number would be 2 because time reversal symmetry gives only 2 well points. Least number of well points one can get from time reversal.
Yeah. So what we will have quantized values is the charge, basically, right? So the topological charge will be quantized. Okay. So the BCD need not be quantized. It can also be a function of the chemical potential, etc. Okay. So just like the anomalous Hall effect. Anomalous Hall effect need not be quantized, even though the Chern number is, basically, right? So likewise, yeah.
Okay, so now then my final question related to all this, that you don't care at all these wild points here, like the band crossing points in your calculations.
So band crossing points can give rise to this physics, definitely. Band inversions can give rise to this physics, etc. Definitely. That's what is happening here, actually. Okay. So it is not specific to band crossing points.
So without band crossing points, then how? I mean, usually, okay, Berry curvature usually gives you band crossing points, right?
Not necessarily. Come on.
Okay.
The simplest example is gapped graphene. That's the simplest theoretical model that you will teach students, basically, right? Yeah. So you add even tiniest of gap delta in graphene, and you will start having this finite Berry curvature.
But then still, that is like a trivial, right? Trivial band crossing point.
See, trivial, yeah, okay. So trivial in what sense? In a Chern sense, trivial, but you can still define a valley Chern number for these.
Okay.
Okay, so the conventional, topological charge description doesn't work. In that sense, they are trivial, but I can still define a valley Chern number. Okay, so for example, in these materials, I can measure non-local valley Hall effect, basically, right? Which is like the proxy for anomalous Hall effect, measuring the Chern number. This is the proxy for valley Hall effect, measuring the valley Chern number.
Okay, so one quick point, maybe there must be. So without any band crossing points, can we get like anomalous Hall effect? Like just I'm not convinced this Dirac point. You see that's not a band crossing point. I still consider Dirac point.
See, Dirac point is a band crossing point. I have no doubt. Yeah.
You can do it during tea time. This you can go on and on. So let's take a quick question from
even
Avdesh.
Better give me a call, actually.
Yeah. Avdesh, you have been raising hand, and the remaining questions will please raise them during tea time. Okay?
Hello, sir. My question is that when you are taking the A's, when you are calculating the anomalous Hall effect, anomalous Hall conductivity, there you are just summing over the Brillouin zone in your all valence band. Then
Correct.
they are taking the linear and non-linear part of your Berry curvature. Both.
No. So wait. So okay. So Berry curvature is not linear or non-linear, right? Berry curvature is defined equilibrium, so it's fixed, basically. Okay.
So when you are
so transport, I can have linear response or non-linear response.
Okay. Then when you are derivative with respect to your momentum space, I mean the Brillouin zone, then there, near the Fermi energy, you are saying if Fermi surface effect is there, if your Berry curvature dipole is far from the Fermi level, then that will not affect your transport property.
So generally, all of these Berry curvature hotspots happen to be near the band edges. Okay, generally. Okay, so very broad statement. Okay, so not literally. Okay, so yeah, that's the point basically. Yeah. So wherever, so suppose you sit on this experiment, do this near this Moire bands basically, right? So there's a Berry curvature hotspot here also. So as long as you are sitting near the Berry curvature hotspot, you will see this physics basically. Okay.
But the AC, when if this is below the Fermi energy, then you can spot this one. But the Berry dipole you can spot.
I don't follow the question.
Okay. Just let me interrupt. I think we are really overshot the time and also the tea break. So please, remaining questions, I request you to please contact the author, the speaker directly during tea break, and let us wind up. It's a very interesting talk and very informative talk, and some interesting physics has come up with in relation to the twisted bilayer graphene. And let's thank the speaker for giving a very nice informative talk. Thank you very much.
Yeah, so if there are any questions, you email me. I'll be happy to answer actually. Okay.
Yeah, so with this, we finish this session. So let us thank all both the speakers and the chairman, Professor Swapnil Patel, for chairing this session. Okay, so we meet in 15 minutes, so we will be late by 10 minutes. So we should meet at 11:40 sharp for the next session. Thank you.
Yeah, sorry, Professor Agarwal, this is Avdesh here.
Yeah, Avdesh. Yeah, sure. I'm here.
So couple of
there is tea time, so we can talk definitely.
Yeah, thanks. So one was, I was curious about the kind of strain. Is biaxial strain sufficient here, or one needs to go to
any strain will work actually. Okay, so uniaxial will work, biaxial will work, or even angular strain. Anything you can put, simplest model you can put in will work actually.
As long as we break C3, then it's fine.
As long as it breaks C3, correct? Yeah.
Okay. And then another question about this sign change of the BCD. Do you know if there is any proof for this? I mean,
that's a nice question actually. So I don't have a proof, but I can indicate actually. Okay. So let's take a simplest model of massive graphene.
Yeah.
Right. And the mass is introduced by, let's say, a vertical electric field, right? Right. So if the mass is introduced by a vertical electric field, then you can easily show that as soon as you switch the sign of the electric field, basically, right? You change the Chern number of the bands.
Right.
Just because the Berry curvature itself is proportional to delta, and it changes sign basically. So that's the simplest, example I can give you.
Right. And then then of course, since that has changed sign, so the derivative.
The Berry curvature dipole also changed sign because everything else is analytically same basically, right? Except for the sign, because this is delta by xi k to the power 3/2, if I remember correctly. Right? Yeah. So, and then the rest follows. That's the simplest example, but mathematical proof, not yet, let's say. Okay. I do know, of course, you also know, some examples are already there in the literature, basically, right?
Right. This bismuth tellurium iodide.
Yeah, correct. So bismuth tellurium iodide is one. There's another one I've forgotten, but yeah, I think there's one example in this original paper itself, basically, massive Dirac model.
Right, that model with the with tilted.
It's not written explicitly, but I think they have this sign change. Yeah.
I see. Yeah.
Sir, hello.
Yeah. Please.
Sir, I have a question.
Go ahead. Yeah.
Sir, why we need current with frequency second times of we use? Sir, why only second time of frequency? Why not 3 times, 4 times? How we
get? This is a very nice question actually. So simple thing is, so all of these signals are very difficult to separate basically. Okay. So what I do is I applied a current, I measured a voltage. Okay. And now to know that whether this voltage is coming from first order, second order, or third order is very, very difficult. And experimentally, one way to do it is actually to apply a incoming current with a frequency omega. And if it doubles omega, so let's say I goes as some I0 times e to the power I omega t, okay, the real part of this. So once, I square will go as cos 2 omega t, right? And then you can do lock-in measurements where you separately measure just the 2 omega signal actually. Experimentally, it's easier to measure. Okay. So third order, if you want to measure, so third order also there will be a lot of interesting physics. Third order, if you want to measure, then that is 3 omega signal. Okay.
Thank you, sir.
I hope that explains. Yeah. So lock-in technique, ask any of your experimental friends. Okay.
Okay, sir. Thank you.
Yeah.
I also have a question. Can I ask?
Yeah. Please go ahead. Yeah.
Sir, as we have read that we got flat bands in twisted bilayer graphene also.
Correct.
So what is the role of twisted double bilayer graphene?
Double bilayer graphene is correct. So the only role is number one. My friends in the lab have samples. Okay, but coming to the technical side, so double bilayer graphene has a larger width basically. Okay, so the impact of the electric field can be more. So I can apply a higher potential drop between the lowest level and the top, basically. Yeah.
Okay, so is there change in angle also? The angle at which we are getting flat bands?
Angle you can set in the lab actually. So this is similar angle. So there's slight difference between the twisted twisted graphene and twisted bilayer, but they are roughly similar basically.
Okay, roughly. So if we increase
so the magic angle where you get flat bands happens to be roughly around 1.1 degree.
In both twisted bilayer graphene and twisted double bilayer graphene.
Yeah, so there it happens at around 1.2 degree if I remember correctly, but very similar. Yeah.
Okay. So we can increase the bilayers and we can get the extra, the potential drop you are saying.
Correct.
The additional potential
drop. So more tunability of the band structure.
Okay. Thank you, sir.
And trilayer even more, but trilayer have a slightly different band structure. Okay.
Okay.
So this just gives you more experimental playground.
Yes. Thank you, sir.
Yeah. Okay. Okay, great. So if there are no questions, then I'll also go for my tea. Okay, I'll stop sharing. Yeah, thanks a lot.
Yeah, Professor Thamizela?
I am available.
Sorry, sir. We are a bit late because the last session got over.
Yeah. I attended the last session as well. I know that. So should I need to stop share now? Or?
Fine. It's fine.
Okay, good.
We'll start at 11:40.
Yeah, sure. No problem.
Do I need to apologize for the last session?
No.
sorry. Just couldn't resist.
Because there are many questions, so it's always good.
I like that, yeah, particularly from the students. Yeah, okay. But yeah, go ahead.
Professor Agrawal, can you hear me?
Yeah, hello. Somebody was asking for me.
Yes. This is Nitesh. So I just wanted to. So I was curious about this dipole, wave convention dipole, these bulk systems. WT2 you mentioned, right? Which is like.
Yeah.
So what is special? Do you understand why WT2? Like, what is the?
No. So what you need, essential ingredients are number one, inversion symmetry breaking or time reversal symmetry breaking. Either of these two, okay? And asymmetry in the band structure.
Asymmetry in the sense?
Meaning it should not be circularly symmetric, let's say, or C3 rotation, some asymmetry, yeah. Very difficult to specify, but some asymmetry, yeah. So some mirror symmetry specifically needs to be broken, okay?
So which is not, for example, this classical tantalum arsenide series of wire semimetals. There it is very small, or like
TAs, I have to check. Maybe there, may not be there. I have to check actually. I'm not sure. Yeah.
Because there the single harmonic generation, the second harmonic generation, people studied that it is very large in tantalum arsenide.
Correct. So a lot of these geometric band effects play a very strong role in second harmonic generation also, which is not there in the conventional theory at all actually. Okay. So I'm not sure, but yeah, maybe there's some clue there. Yeah. But a very speculative answer actually. Yeah.
Or maybe WT2 has a van der Waals kind of structure there you can get.
So, but van der Waals has nothing to do with it actually. Yeah.
No, just for experimental thing, like you will have more.
So, WT2, because it was readily available in a lot of labs and it was easy to exfoliate.
Yes.
That's why you will find a lot of papers on WT2. And since there were experiments going on, so, theory colleagues who are privy to that knowledge, they obviously work on that.
Yeah, thank you.
Yeah.
One simple question. I don't know whether it's right or wrong, but you use the word anomalous Hall effect for this, but it's only mainly used in the past when you have a magnetization, right?
Correct. Yes. In the past, it has been used for time reversal symmetry breaking without explicit magnetic field, and ferromagnets would be the conventional example. Yeah, correct.
So can we allow, like in your case, you have nothing like a magnetic field, right? In this.
No. So these were not even magnetic systems. These are time reversal preserving systems actually. Okay. So there the anomalous Hall effect is 0. So you will have this nonlinear signal only.
Oh, okay. Initially, you said nonlinear anomalous Hall effect. So I mean.
So this is anomalous in that same sense, basically, that you do not expect a Hall effect.
Normal Hall effect.
Normal Hall effect, right? In the absence of magnetic field or in the absence of ferromagnetism. So in that sense, anomalous. I mean, it's just name.
Actually, the word is somehow synonymous with the existence of magnetization inside the system.
It is. But yeah, this is just literature's terminology can be confusing. Yeah, I'm just sticking to what people, more knowledgeable people than me use actually in the literature. Let's say. Okay. Yeah, and it is advantageous also just to keep the same terminology, as long as you understand what it means basically. Yeah. But it can be confusing to younger colleagues.
Sorry for interrupting, but I think we should start the second session of this conference on the second day. So the next session has 3 talks, and this session will be chaired by Professor Surjit Singh from IISER Pune. So Professor Singh, you can start the session.
Hi, thanks a lot. So hello and welcome to the second session of the day.
Yeah, sorry. Again, so I just announced important information that speakers who do not want their data to be stored in YouTube, they can tell us. We can remove the talk from the YouTube. Okay, thank you, Professor Singh.
All right, so we have 3 presentations in this session, and the thrust of the session is on materials, on the crystal growth. And the first talk is by Professor Arumugam Thamiyavir from Tata Institute of Fundamental Research. He's an eminent crystal grower, a leading one from the nation. So he is going to talk about crystal growth of topological semimetals. So I will invite him to start his presentation. Professor Thamiyavir, you can start.
Thanks, Dr. Surjit Singh. Good morning to everyone. At the outset, let me thank the organizers for giving me this opportunity to present some of our latest works. As you know, the topological semimetals have recently got lots of attraction because of this availability of high performance computation facilities, where lots of database is available right now. And these band structures which have been predicted have to be characterized using high quality single crystals. So the single crystals are very, very important to study the ARPAs and other transport physical properties, anisotropic transport physical properties. So in this talk, I'm going to highlight how to grow the single crystals of these topological semimetals. Okay, to start with, sorry. Okay, let me start with an acknowledgement. These works are done by 2 of my former postdocs, Dr. Matin and Dr. Rajiv Mandal. Dr. Matin is again working in a college in West Bengal, and Rajiv Mandal is working in UGCDA CSR Kolkata as a scientist B. And this work is done in collaboration with my former senior colleague, Professor S. Kedar. And some of the works of today, which I'm going to present, is done by my doctoral student, Mr. Sauvik Sasmal, and Ruta Kulkarni is my scientific officer. And the theoretical inputs are given by our young colleague from DCMPMS TIFR, Dr. Baldev Singh. Okay, the plan of the talk goes like this. I'll start with a very brief introduction about how to grow, what are the various techniques that are available to grow the single crystals of topological semimetals. And I will go in detail some of these crystal growths of this WSI2 and this calcium copper Sp, which has some interesting results. So I'm going to discuss more about the transport properties of WSI2 and calcium copper Sp. Finally, I will summarize these results. Okay. So crystals can be grown by a variety of methods. Particularly these topological semimetals have to be grown at high temperatures. I mean, these cannot be dissolved in some low temperature solvent or something like that. So essentially all these crystal growth techniques involve relatively higher temperatures. For example, we can grow a single crystals by Czochralski method if the material is melting congruently. If the material is melting incongruently, then the material has to be dissolved in some solvent and it has to be grown by a flux method or a high temperature solution growth method. Sometimes some of the materials have high vapor pressure, and in those cases, the materials, although it is congruently melting, these can be grown by Bridgman method, which is again something similar to a Czochralski method, but there are some differences. You employ 2-zone furnace and all these things. And many of the materials recently, people have attempted various systems to grow them as single crystals by using vapor transport. So the idea of this vapor transport is that you make the material, you put a transporting agent, you keep it in a 2-zone furnace and keep it one from the hot zone. The material goes to the cold zone and it crystallizes here at the cold zone. So in today's talk, I am going to highlight this Czochralski growth and the flux growth. The crystals that we have grown by these 2 methods, I will show some of the examples. So before I proceed further, we need to we need to understand the phase diagram. As I told you in the previous slide, so I have mentioned some of the words like congruent melting and incongruent melting. So we need to understand what is a congruent melting and what is an incongruent melting. This, if you consider the phase diagram of silver and neodymium at 1:1, at 50-50 concentration of silver and neodymium, you see that it melts, this 1:1 silver neodymium melts at 952 degrees centigrade. And if you heat it above this melting point, everything will be in liquid. And when you cool down, it crystallizes in the same composition. It doesn't dissociate into any other phases. On the other hand, if you take silver 2 and neodymium in the ratio 2:1, if you go to the melting point and come back, it dissociates into multiple phases. So this is incongruent melting. So the congruent melting compounds can be grown by Czochralski method, that is directly from its melt, whereas the incongruent melting compounds has to be dissolved in some solvent. And for that, you need to find out what is the suitable solvent. And some of the few other points in the phase diagram. This is a composition which has the lowest melting point of this silver and neodymium for this 80-20 ratio, and this is called the eutectic composition. The eutectic composition means it has the lowest melting point in this phase diagram. So sometimes we take advantage of this eutectic composition, and we use this as a solvent to grow the crystals using this high temperature solution growth or the flux growth method. So recently, this compound cobalt silicon has attracted lots of interest because it is a spin 3/2 Raritas finger 5 fermion, and it carries the highest Chern number +4. And people have grown these crystals using a third element, tellurium, as a flux. And you can see the size of the crystals is about 1.5 millimeter by 2 millimeter. It's a very small size. And see, this has been grown using a third element, tellurium, as a flux. Sometimes using this kind of third element as a flux also incorporates some defects or some impurities inside the crystals. So it is also always better to grow the crystals from the stoichiometric melt or from a self-flux, because in this case of cobalt silicon, it has a highest melting point, and you can see that it is congruently melting. It congruently melts at around 1450 degrees centigrade. So this can be grown by Czochralski method. And we have grown this single crystal of this cobalt silicon, which is fairly a long crystal, about 7 centimeter long. And these are the Laue diffraction pattern of these grown crystals. And we have already studied the physical properties, but this is just to show that the congruently melting compounds can be grown by Czochralski method. And similarly, in the same category, cobalt silicon, PT aluminum, it also melts congruently. You can see that it melts congruently at 1550 degrees centigrade. And this can also be grown by Czochralski method. But one of the difficulties in growing this single crystal is that the aluminum has a high vapor pressure. And you can see that after the growth, the chamber is completely filled with this aluminum vapor. But still, we can get a very large single crystals of this PT aluminum. We have grown these single crystals, and we have studied the transport properties. But in today's talk, I'm going to highlight the work on our WSI2 single crystals. This tungsten disilicide, which has a melting point around 2160 degrees centigrade, it melts congruently, and it can be grown by this Czochralski method. So for this Czochralski method, you need to have a tetra arc furnace. What we are having in our lab is that we have a tetra arc furnace. The material is taken in a copper hearth, and something around 7 to 8 grams of this material is initially melted and flipped over several times. And we cut a seed crystal from this polycrystalline sample, and a seed crystal is inserted into the melt, and then it's slowly pulled. So essentially, as soon as you dip the seed crystal into the molten material, you can see that the multiple grains are getting solidified near the seed, and you make a necking so that you allow only one grain to grow into a large single crystal. So this is how during the growth, the crystal growth looks like. And you can see that this is a polycrystalline seed crystal, and from here, the single crystal has been grown. And this shows the Laue diffraction pattern corresponding to 100 and 001 directions. This is a tetragonal system. So the first thing we did was we powdered the sample, and just to check the phase purity, whether there are any impurity phases or something like that. We found that the WSI2 is totally phase pure, and we have estimated the lattice constant from the powder diffraction data. And this is this crystal structure. It crystallizes in the centrosymmetric space group I4 bar mm, body-centered space group I4 bar mm. And these are the Wyckoff positions of tungsten and silicide atomic positions. So after orienting and cutting the crystal along the crystallographic directions, we have passed the current along 100 direction and applied a transverse magnetic field along 001 direction. Similarly, in this case, we passed the current along the 001 direction and applied the magnetic field along the transverse direction, namely 100. You can see that the electrical resistivity decreases very rapidly from 100 Kelvin to 15 Kelvin. It follows a very steep decrease in the electrical resistivity, and it remains almost constant. This is the residual resistivity. So the rho zero residual resistivity is less than 1 microohm centimeter. The residual resistivity ratio is 160, which indicates a high quality single crystalline sample. And the interesting feature here is that, like tungsten ditelluride, it also shows an increase in the electrical resistivity as we apply a magnetic field. And you can, at a 14 Tesla magnetic field, the electrical resistivity is almost 2 to 3 orders of magnitude larger here. And one of the other things is that there is a very little anisotropy in the electrical resistivity. For example, for J parallel to 100 and J parallel to 001, at room temperature, the absolute value of resistivity is almost very close. I mean, about 15 microohm centimeter in both the cases. One of the oldest studies have also mentioned a similar thing. Here they have measured the electrical resistivity up to 1000 Kelvin. At around 300 Kelvin, the anisotropy between the basal plane along the z-axis is almost very small. Okay, so this type of increase in the electrical resistivity with the applied magnetic field has already been seen in several of these topological semimetallic systems like lanthanum antimony and lanthanum bismuth. And this, where the electrical resistivity shows an upturn like metal insulator transition, they coined as this TM. And where this saturation is observed, this is an inflection point. So based on this, they have constructed a triangular phase diagram. And this is a universal triangular phase diagram. Irrespective of the chemical and structural differences, you are seeing this kind of triangular phase diagram in many of these compounds, like, for example, lanthanum antimony, lanthanum bismuth, and platinum tin 4 and WTE4. All these compounds, which are showing extremely large magneto resistance, exhibits this type of triangular phase diagram. Even in our system, tungsten disilicide, we have also seen similar kind of triangular phase diagram. The magneto resistance is also quite large. At a magnetic field of about 14 Tesla, it reaches around 2 into 10 power 5% of magneto resistance, which is extremely large, something similar to that observed in WTE2. And the main reason for this is attributed to this perfect electron-hole compensation here. You can see that in both the directions, you are observing a large magneto resistance. The interesting thing is that we have also observed DeHaas van Alphen oscillation studies, and this was measured at 35 millikelvin. This was done in collaboration with our IMR Tohoku University, where they have also done this angular dependent studies on our samples. You can see this very nice DeHaas DHPA oscillations in this sample. And for H parallel to 100, there are 3 different frequencies, and H parallel to 001, there are these are the 3 different frequencies that we have observed. And based on this, we have constructed this Fermi surface properties. Like here, you can see that this is the experimentally observed angular dependence of the DHPA oscillation. This is the theoretically calculated angular dependence of DHPA oscillations. The experimental and theory are exactly matching with each other, and this has a dumbbell-shaped whole Fermi surface here. And also in the other direction, you have this electron Fermi surface, and these are seen in this here. There B1 and B2 are indicated by these 2 frequencies, and B3, this electron packet, is indicated by this frequency here. The interesting feature in this WSI2 is that it shows an anisotropy, large anisotropy in the Hall effect. You can see that at 2 Kelvin, the Hall resistivity shows a nonlinear behavior, indicating a multiple type of charge carriers. If you pass the current along this 001 direction and field along this 100 direction, then it shows a very linear electron dominated Hall effect here. So this type of anisotropy in the Hall effect has also been observed in some of the other systems. So recently, in the sodium tin 2 arsenic 2 single crystal, which is a single band system with open Fermi surface, they have also observed a similar type of anisotropy in the Hall effect, and they have coined a new word called Goniopolar effect. So, but here, one of the constraints, one of the things is that it should have a single band system with open Fermi surface, but ours is not a single band with open Fermi surface. So, but still, we see a large anisotropy in the Hall effect. That is because of the anisotropy in the Fermi surface. Okay, so then let me, so far these WSI2 has been grown by Czochralski method. Now let us focus on this, the other method of crystal growth, namely the high temperature solution growth or the flux growth. So as I told you already, those materials which are incongruently melting can be grown by this high temperature solution growth method. Like for example, let me give an example with platinum tin system, which Adam Kaminsky was also mentioning this morning. So you can see that there are many phases of platinum tin in the tin rich side. You can see this platinum tin 4 is here, and platinum tin 2 is here, platinum 2 tin 3, and platinum tin. So this is platinum tin is congruently melting. Of course, you can also grow this single crystals by using excess tin as a flux, but the growth has to be stopped at around 900 degrees centigrade. So if you want to grow these single crystals of platinum tin, you can take platinum and the tin rich side, and you can stop the growth at around 900 degrees centigrade. On the other hand, if you want to grow the single crystals of platinum to tin 3, you can go to higher melting point of this around 1050. Cool down very fast, enter into this region, and then cool down in this region very slowly, then you will have platinum to tin 3. And similarly, if you want to grow this platinum tin 4, you don't need to go to very high temperatures. You can go to around 800, 900 degrees centigrade and then come down very rapidly and then cool down in this region to get platinum tin 4 single crystals. So high quality platinum tin 4 single crystals can be grown by this excess tin as flux. So typically, when you're employing a flux growth method, one of the conditions for this flux is that the flux should have very low melting point, so that we can easily remove the flux and isolate the single crystals after the growth. So typical fluxes that are used are this kind of lead, tin, and bismuth, antimony, indium. These are having low melting point of in the temperature range between 150 to 700 degrees centigrade, and it is very easy to do the centrifuge at high temperatures if you are using either one of these materials. And it is better to use one of the constituents as a flux, or that is called the self flux. So if you're using third or fourth element as a flux to grow a single crystals by flux method, then the questions of this impurity concentration entering into the crystal all come into picture. So for example, we have grown this calcium copper antimony by employing a flux method. So in this case, we can use antimony as a flux to grow this crystal. But when we grow the crystal with antimony, excess antimony as flux, one of the problems is that calcium antimony phase is very easy to crystallize, and we are getting those crystals. So in order to avoid that, we have to increase the concentration of copper. And when we found the copper antimony phase diagram, we found that the copper and antimony has a eutectic composition at around 526 degrees centigrade. And we can take an advantage of this eutectic composition to grow the single crystals of calcium copper Sp. So the starting composition for this calcium copper Sp is that we have taken the ratio 1:4.5:7.5. And we have followed this temperature profile. We slowly heated up to 1050 degrees centigrade, held at the 1050 degrees centigrade for about 24 hours to ensure a proper homogenization. And then we slowly cool down at the rate of 2 degrees centigrade per hour. And we have centrifuged the single crystals at around 625 degrees centigrade, about 100 degrees above the melting point of this eutectic composition. So we have got a very nice single crystals of this calcium copper Sb. And the first thing we did was we confirmed this single crystals using this Laue diffraction. And this Laue diffraction shows that the 0001 plane of this hexagonal system, and well-defined Laue diffraction pattern confirms the good quality of the single crystal. You can see this, the experimental and the theoretically observed patterns are exactly matching, confirming the 001 plane of this flat plane of the crystal. So this is the crystal structure of this calcium copper antimony. So the calcium layers are separated by these copper and antimony layers. And we found from various studies, this copper and antimony layers are important for this transport properties in this system. And we find that these are the main reasons for this observed transport properties in this system. So The lattice constants are given by these parameters, and we can see that there is the powder X-ray diffraction is completely phase pure without any impurities, and these are the Bikov positions of this calcium copper antimony system. The electrical resistivity is highly anisotropic. As you can see that when we pass the current along the basal plane, the electrical resistivity is following this red color curve. And if you pass along the current along the C-axis, the electrical resistivity is very large, it's the order of milliohms, but here it is of the order of a few hundred microohms. So there is a large anisotropy in the electrical resistivity. So the anisotropy amounts to 37 at 300 Kelvin. And this shows a typical metallic behavior. The electrical resistivity follows a typical metallic behavior. And the interesting thing comes in the Magneto resistance. The Magneto resistance at high fields is quite linear, and then at low fields it shows a huge drop. And this type of the Magneto resistance is also highly anisotropic when you pass the current along this basal plane and along the C-axis. And this type of huge cusp-like behavior is seen at low fields along the 001 direction, which shows that it shows a weak anti-localization behavior. And this large anisotropy also signals that there is a quasi-two-dimensional nature of transport in this compound. So we have calculated the magneto conductivity using this expression, and we can see that the magneto conductivity can be fitted to that usual HLN model. So we can see that the fit is quite nice here, and we estimate this, the alpha parameter is of the order of 4 × 10⁶. So this is typically observed in most of these three-dimensional systems, where it also represents the number of conduction channels present in this calcium copper sp. And we attribute this conduction channels are due to this copper and antimony layers present in the system. And the phase coherence length is estimated as 53.6 nanometer. And you can see that as the temperature dependence of this alpha and phase coherence length, the number of conduction channels remains almost the same as you increase the temperature, whereas the phase coherence length decreases because of these phonons. So we have also, in order to qualify this calcium copper sp as a two-dimensional transport property, we have measured the angular dependence of this calcium copper sp, and we found out that the normalized conductivity, as you change the angle, they fall onto a single curve. So this confirms the two-dimensional nature of this weak anti-localization, and this is because of the two-dimensional conduction channels are presumably due to these copper and antimony layers here. So we have measured this linear resistance in high magnetic fields. You can see it's from 10 Tesla to 14 Tesla. You can see this Cherenkov-de-Haas oscillations, and after background subtraction, you see a very nice STH oscillations here at T equal to 2 Kelvin, and you can see a very single, only one unique frequency at 314 Tesla, and this STH oscillations can be fitted to this LK equation. As you can see that this is the from the fitting we can estimate the various quantum parameters. So these are this.
Sir, I will. Yeah. Sorry, you have 5 more minutes to wind.
Yeah, sure. So we have the temperature dependence of this calcium copper antimony is shown here. As this temperature is increased, the frequency of the oscillation decreases. And from the temperature dependence of this FFT amplitude, we have calculated the mass as 0.4 m0. And from the field dependence, we have also calculated the dingle temperature as 8 Kelvin here. And the angular dependence has also been done, and it follows the 1 over cosine theta formula, which confirms that the two-dimensional Fermi surface nature of this calcium copper antimony. So this band structure has been done by Dr. Singh, and these experimental and band structures are very much matching with each other. We can see that there are whole bands are dominated by antimony p states, and the electron bands are composed of copper s states, and there is no band inversion or non-topology, and this is a non-topological semimetal. And the interesting thing is that there is a very small density of states at the Fermi surface, and there is very small density of states of calcium, whereas there is a notable density of states for copper and antimony. So this suggests that the copper and antimony may be the conduction channels in this calcium copper antimony system. And since these copper and antimony layers are the conduction channels, we have measured this Hall effect and you can see these very subtle oscillations up to 14 Tesla and quantum oscillations, and this corresponds to the quantum Hall effect. So in order to confirm the quantum Hall effect, we have measured the Hall effect up to 45 Tesla in a high field magnetic laboratory, and this was measured at 1.8 Kelvin. We can see very nice quantized Hall steps here. Although this is a bulk system, this exhibits this quantized Hall effect, and so you can see that when we plot it as 1 by rho xy versus 1 by b, we can see this very nice quantized Hall steps. And from the step size of this Hall effect, one can calculate the number of conduction channels. And this is the number of conduction channels. From the number of conduction channels, we can calculate the bulk carrier density, which is amounting to 5.43 into 10 power 26 per meter cube. And if you measure this Hall effect, and from the usual Hall effect thing, we can calculate this carrier density as 5.8. These two bulk carrier density measured by the Hall effect and this one are perfectly matching with each other. So these steps are indeed quantized Hall steps. So to summarize, the single crystals of topological semimetals can be grown by a variety of methods. From the transport studies of WSI2, we find that it is a perfectly compensated semimetal, and the Hall effect shows very highly anisotropic, and calcium, copper, antimony exhibits two-dimensional nature of charge carriers. The high magnetic field Hall data reveal quantized Hall steps in calcium, copper, antimony. So these results are published in these two different papers. If you want, you can have a look at it. Thank you very much.
Thank you very much for a wonderful talk, especially the data that you showed on calcium, copper, antimony is really exciting. And also thanks for finishing on time. So the talk is now open for questions from the audience.
Yeah, I think from online audience, there are two hands I can see they are raised.
Okay.
Okay.
Can you invite them to ask their questions?
Yeah. Professor Sahadas Gupta, you can ask your question, please.
Yeah. Am I audible?
Yes. Go ahead.
Yeah, Professor Thanitsabal, I just wanted to ask about this calcium copper antimony, which is really a nice system.
Yes.
So there, as I can see that conduction is primarily from antimony, right?
Copper and antimony.
Yeah, I mean the copper has probably, is the copper nominally in 1+ state or which kind of state? Of course, it's a metallic system.
Yeah. So it is a metallic system, but I don't know the exact valence state of copper. But we believe that we see from the density of states, we can see that there are copper and antimony states available near the Fermi energy.
Yeah, but that's because of the hybridization of probably this empty copper S with antimony. So it is because of just this hybridization. So the whole thing is non-magnetic, right?
Yeah, of course, it's non-magnetic.
Yeah. So then probably it is primarily from antimony. I mean, of course, the copper S character is possibly just the hybridization effect. Thank you. Thank you very much.
Swapnil, you can go ahead and ask your question.
I just have a simple question. This WSI2 system is showing no anisotropy in the resistance, but it is showing a large anisotropy in Hall effect.
Yes.
So
you can see that. So you can see this. This is the, if I apply the magnetic field along the C-axis, it is dominated by this hole, and in the AB plane, it is dominated by this electron Fermi surface. So you can see that is the reason why you have this both. There are multiple carriers, but on the other hand, if the magnetic field is along 100 direction, and the current is along 001 direction, you can see this Hall effect is completely electron dominated.
Okay. So it's just the change of the sign of charge carriers that should matter. They may make a difference.
Yes.
But as far as the data which shows and no anisotropy, that is, I think, the pure resistivity, right?
Yeah, that is purely resistive.
Okay,
longitudinal
so it doesn't
resistance.
matter. So
Yes.
whether it's a sign of charge carrier. Okay.
So we have a question. We have time for one more quick question. If there's one.
One question. Professor Telluride, thank you for very informative talk.
Yes.
So For Swarovski method, is the seed crystal, should it have any particular properties or?
No, it is a seed crystal is the same material. I mean, we cut the seed crystal from WSI to polycrystalline sample.
So usually doesn't have to be seed crystal.
See, to start with, you may not have a single crystal. So that is why when you insert the seed crystal into the mint, you will see large number of grains here because of this local solidification. And you pull the crystal a little faster and increase the temperature, you make a necking. This necking process allows only one large grain to grow into a crystal. So this process is important if you are using a polycrystalline seed.
Okay, thank you.
So I have a very quick question related to the crystal growth.
Yes.
How do you cast these feed rods, the polycrystalline seed? Do you have a casting system where you use induction melting? Or
No, we don't use a. See, we make a huge amount of this polycrystalline sample. We cut it using spark corrosion cutting machine.
I see. Okay, that's nice. Thank you very much for a very nice talk, and for finishing it in time. Everything is perfect. So thanks a lot. I would now like to invite the next speaker, Professor Kaustubh Manna from Indian Institute of Technology, Delhi. Kaustubh, are you around?
Yeah.
Okay,
I'm
great.
just sharing host disabled participant screen sharing. I'm not allowed for screen sharing.
Okay, that problem will be solved in a minute. Can anyone from the organizing team take care of this? Give him permission to share his screen.
Yeah, now I think I can share. Yeah, share. Yeah, is it visible now?
Yes, it is visible. Yes.
Yeah.
So Kaustubh is at IIT Delhi, and he's going to talk about anomalous Hall effect in topological quantum magnets. Kaustubh, you have 25 minutes for the presentation and 5 minutes for question answers. After 20 minutes, I will give you a signal. So
sure. Thank you. So, so first of all, I'd like to thank the organizers for arranging such good conference and inviting me to give a talk in this conference. So it's really nice hearing to all such nice talks. So let me start. So I'm Kaustubh Manna from Physics Department, IIT Delhi. I just recently joined here 1.5 years back. So while so first of all, I would like to thank to all of my collaborators who are part of this work, and I really thank them because I really feel fortunate to be part of their team somehow. And so today's talk, I thought I will discuss a little bit of our recent contribution, recent development in the field of quantum magnets. So here we observe the linked loop quantum state. So this is the theme of the today's talk. So I don't think I need to give a really detailed introductory slides to this audience, but I'll definitely present a background study of like the approach that we follow to identify these linked loop states in a quantum magnet. So quantum magnet means all the materials that I'm going to talk here is the magnetic materials, and how we observe them, and what is the consequence of these quantum states on the physical properties, and how we observe that. So that I'm going to discuss today. So the RPS part of this talk is mostly done in collaboration with Professor Jahid Hassan from Princeton University. So let me start. So this work is just accepted in Nature just a few weeks back, and I hope it will appear maybe next month sometime, but let's see. So I'm not going into very detailed introductory, but just to give a overview that based on the strength of the spin orbit coupling, crystal symmetry, etc., so we can broadly classify different topological materials in this pattern. Like once we have the band inversion and we have the protected band crossing, we have the nodal line. Then depending on the spin orbit coupling, strength of the spin orbit coupling, we can have either the bulk gap but protected surface state, it's like a topological insulator, or in the bulk we can have protected band crossing like Dirac or Weil semimetals. Now this Dirac semimetal case, we have this fourfold degenerate band crossing. Whereas for the wild semimetals, we can have this twofold degenerate band crossing, which comes because of the either broken time reversal symmetry or broken inversion symmetry. Now, these wild fermions, whatever we are talking about, these are really special quantum states, like they act as a source and sink of the very curvature, and on the surface they have these protected surface states. These are called the Fermi arc surface states. Now, in the literature, there are a lot of examples of these broken inversion symmetry states, like compounds like tantalum arsenide, this entire family of compounds, it was already shown. And recent addition to this family is the topological chiral crystals. So this is just our recent discovery, and these are very few publications from our recent work, and where we have shown that these are really a special class of compounds where we have the chiral symmetry, like the broken inversion symmetry, and we can have the Fermi arc which expands the entire Bilayer zone. And these are very special class of compounds in the sense that it carries lot of promises, like it can have the chiral magnetic effect, or in the magneto-optic studies you can have this quantized circular photogalvanic response, etc. So those investigations are going on right now. But these are all the family of compounds where we have the wild fermions because of the inversion symmetry broken conditions. The other class that is present is the broken time reversal symmetry. That means these are the magnetic materials. So recent example is this cobalt 3 into sulfur 2, these materials, where these are the magnetic materials. So in the sense, these are ferromagnetic materials. So we have broken time reversal symmetry. But today's talk, what we are going to focus is that these are the wild fermions, in the sense that these are the magnetic materials, but it is not like discrete wild points, but we have wild loop. Okay. So in the talk, I shall explain you what is the speciality about this wild loop, or why we are calling this as a wild loop. But let me tell you that this appears as a consequence of the ferromagnetism in the material. So since these are magnetic material, we have the singly degenerate bands, and we are playing with the spin orbit coupling, like strength of the spin orbit coupling, which results to this wild loop. So wild loop means we have these two bands which is crossing, and this is this magenta, this line is the crossing line. Okay, and this nodal line, this is called the wild loop in this case. So the class of material that I'm going to focus on is actually Heusler compounds. So Heusler is basically a family of compound, and this is generally represented with this formula X2YZ, whereas this color code shows which are the elements that can go into this X, Y, or Z sites. And this family of material is very famous for its high tunability, in the sense that in the X site or Y site or Z site, we can easily dope with the other elements. And as a consequence, as you can understand, that we are playing with the number of valence electrons in the system. As a consequently, we are playing with the Fermi energy, like Fermi energy can go up or go down. And by substitution, actually, we are changing with the crystal symmetry also. So as you see, a lot of tunability is present in this class of materials. And consequently, it is shown that with this kind of doping or interplay with the crystalline symmetry, we can achieve a lot of these exotic physical properties in this family of compounds. So this family of compound, Heusler, are a really special class of compounds, and we are focusing on a particular type of full Heusler compounds. So these compounds are this cobalt 2 full Heusler compound, like cobalt 2 YZ. This Y and Z are these are the different elements that can go into the Y site or Z site. And these cobalt 2 based full Heusler compounds, they are crystallized with this FM bar 3M space group. So these are the cubic crystal structure, and we can have lot of mirror symmetries. For example, in the real space, the atomic arrangement can give rise to these mirror planes, which results in this particular mirror symmetries like MX and MY, MXY mirror symmetries in the Brillouin zone. So they are actually linked with the real space and the momentum space. They are linked. This atomic arrangement, as we change the atomic arrangement, we can play with by whether these mirror symmetries will be protected or not. Consequently, in the momentum space, these mirror symmetries will be protected or not is directly connected one-to-one correspondence. Okay, but the key point here is that because of this particular crystalline symmetry, we can have the protected inversion symmetry in this class of materials. And in 2016, this through theoretical paper, they predicted that in this particular class of compound, we can have 3 nodal lines because of the band crossing, which are protected by this particular mirror symmetry. And when you incorporate the spin orbit coupling, depending on your magnetic direction, you can have the wild points, which forms in arbitrary position in these compounds. We pick this class of material and focus our study to a particular compound, which is this cobalt to manganese gallium. So this compound, cobalt to manganese gallium, so this crystallized in F-Barthian space group, and here in the band structure, we have observed that very close to Fermi energy, we have this band crossing, and which is particularly protected by these 3 mirror symmetries. Consequently, in the Bilayer zone, because of these 3 mirror symmetry, we can have 3 nodal lines. And this picture is without considering SOC, this spin orbit coupling. Now, once you incorporate the spin orbit coupling, then spin is no longer good quantum number of the system. So crystal symmetry reduces depending on where the spins rise. Okay. So let's assume that you have applied magnetic field and you have polarized the spins along the z direction. As a consequence, now mx and my are no longer the mirror symmetry of the system. So there is nothing to protect these mirrors. There is no particular to protect these nodal lines. So it gaps out. And once it gaps out, it gives rise to strong contrast of the very curvature. But there is a catch here. Point is that this material, as I said, that these are ferromagnetic material, and ferromagnetic material means these bands are singly degenerate bands. And when these bands are crossed with each other, then like the wild points, we have the linear band crossing just above and below the band crossing. Second point is that this material, the cobalt to manganese gallium, as you see that the strength of spin orbit coupling is really weak because the cobalt, manganese, and gallium SOC is really weak. As a consequence, there is a question whether this band, which was there earlier protected, whether it will be actually gapped out or not. And experimentally, what we observe is that this gapping of this nodal line is really beyond the experimental limit. So in practical, what you have is that 2 singly degenerate bands which are crossing with each other, and we have these line nodes which are dispersing throughout the Bilayer zone. And this line node above and below, you have the dispersion like the wild points. And this is why, in connection with the wild point, we are calling this as a while loop. Okay. Now let's see what is the consequence of this while loop on the physical properties, and then we'll go into the practical, like experimental detection of this while loop, how they disperse and how they are distributed in the Bilayer zone. So to do that, first we grow the single crystal. So this single crystal I have grown using the Bridgman technique, and then this is the oriented single crystal along z direction. And when we do the magnetic characterization, as you can see that this is a high temperature ferromagnet, like a transition temperature is nearly 700 Kelvin. So at room temperature, this is a ferromagnet with magnetic moment nearly 4 MeV. Okay, so this is a room temperature ferromagnet. That's the key message of this characterization. Next, we do the electrical transport measurement. So this is the configuration for the electrical transport, and we measure the Hall resistivity. So this is the field dependent of Hall resistivity, and we use this formula to calculate the Hall conductivity. So from the field dependent of Hall conductivity values, so we extrapolate the high field value to a zero field, and this value gives rise to the anomalous Hall conductivity value for this compound. And when we compare the anomalous Hall conductivity with the other compounds that's reported in literature, as you see, our compounds lies on the top. So this is one of the largest anomalous Hall conductivity material ever reported in literature. Second thing is that how much this anomalous Hall conductivity is robust with respect to the temperature fluctuations. So we record the anomalous Hall conductivity values with respect to temperature, and as you see that even up to room temperature, the value does not decrease drastically. And when we estimate the Hall angle, which is from this formula, you see that Hall angle increases with temperature, and it is practically maximum around the room temperature. This clearly gives indication that the protection of the anomalous Hall conductivity or the topological states with respect to the temperature fluctuation is really robust in these compounds. Okay. Next is to detect the topological states that we have been talking about in this material. how it looks like, that we want to look into. But before that, we are doing this thermal. So that was the electrical transport. So we do thermal transport also. So thermal transport means we replace the current with respect to temperature gradient. We create a temperature gradient and we look into the voltage drop. So like the anomalous Hall, here we calculate the Nernst thermopower, which is the voltage drop with respect to temperature gradient. And when we do a field dependent of Nernst thermopower, again we extrapolate the high field value to a zero field value, and this is the anomalous Nernst thermopower value. And when we plot with respect to temperature, as you see, the anomalous Nernst thermopower is increasing with temperature. Okay, this is very surprising. And when we plot the room temperature value with respect to the Nernst thermopower signal for the other compounds reported in literature, as you see, our compound lies on the top, and this is in the log scale. So room temperature value, whatever it is, we observe it is already 6 times larger than any compound ever reported in literature. And since the transition temperature is 700 K, so we don't know where it will stop, because we had the measurement facility until room temperature. So this is really exotic, as you see that the topological, like the physical properties are really exotic. Now next we want to look into the topological states which gives rise to these exotic physical properties. So for that we take the help of the RPS measurements. So this is the schematic diagram where we show that there are two bands which is crossing, and there is this band crossing is protected by the mirror symmetry. So we have this nodal line, and which also gives rise to the surface state, because if it is a wild line, then you should have a surface state also, which is called the Graham surface state. Okay, so this is the Fermi surface which we measure, which shows that there are a lot of complex features. And when we'll compare with our theoretical calculation, we see that all the features are exactly reproduced. Indeed, these are the points, that these different color codes, this shows that these are part of different nodal lines. So I'll just after a few slides I'll come back to these, like these different color nodes, what it represents, like what are the different nodal points or nodal lines we are talking about. But as you see that there are finite contribution of the nodal lines at the Fermi energy. So to do that, to whether this is a band crossing really or not, we look into different plots and different ky values, and we do their energy dependence. And as you see that the crossing point, there is a finite crossing point, as you see here, just below the Fermi energy, and it is holding true for a range of ky values. So this is a distinctly different behavior compared to the Weil or Dirac points, because for Weil or Dirac you should expect crossing point at a particular kx or ky value, not for a range of ky values. So this clearly gives the indication that whatever topological state we are looking at is actually a line node. Okay. Then we look into the energy dependence vertical cross sections. Okay, we just go from top to bottom as we change the energy. So when we on the top, we have this kind of feature. As we lower the energy, we hit the nodal line and it points, it forms a point, and as you go into deep, you have the opposite kind of feature. So together it gives a clear indication that whatever we are observing in this material is the topological states. This is the first observation of the topological states in the room temperature ferromagnet. So this work was actually done back in 2016 or 2017, but that time nobody believed us, because we had really tough time convincing to the referees. Even it was rejected by several journals that they don't believe existence of the topological states in a ferromagnetic material. But finally it was published in 2019. But next step is that how these nodal lines that we are talking about, how it disperse in the Brillouin zone, how it changes, like how is the network of the nodal line in the Brillouin zone. That is the next approach. So for that, what you do is that, so this is the Brillouin zone, and as I said that this is a cubic crystal, so we have a lot of symmetries. And so to map the details of the dispersion of the nodal lines in the entire Brillouin zone, what we do is that we prepare the single crystals, and this is a 3D crystals. So we orient the crystals along different directions, and we cut the crystals in the shape of rods along different directions, like 100, 110, and 111 directions. And then we cleave the crystals in situ within the chamber for the RPS beam time in the beamline. And then we do a energy dependence as well as angle dependent investigations. and then we map the information for a particular fraction of a Bilayer zone. Then just apply the symmetry, the mirror symmetry, and repeat that information into the entire Bilayer zone. That is how we get the picture how these nodal lines are dispersing in the throughout the Bilayer zone. So these are the three Fermi surfaces, as you can see on the different axes, as I see here, containing x1, x2, and x3. So this is, we take the 001 direction oriented single crystal, just clip the crystal, then you get this Fermi energy, Fermi surface, where you can see that there is a distorted square kind of feature. Second thing is that when we want to map it along the other surface x2, what we do is that we take the same sample, then we do a energy dependence, and this energy actually we vary from like 500 eV to 800 eV. Then we get a energy dependence along the kz direction, then we get a component along kx also, and this is how we generate the kx versus kg plot in this information for the Bilayer zone. The same goes for ky also. Sometimes we rotate the crystals also, and we record the angle dependence as well as the energy dependent plot, and then we get the feature of kx1, x2, and x3. Ideally, because of the crystalline symmetry, like because this is the cubic crystals, right? Ideally, x1, x2, x3 should be identical, but there are little bit difference depending on our like the plots and the energy etc. So there is slightly difference in the plots, but more or less you can see that the features are it's the same basically. Next, when we want to discuss about the detailed dispersion of the nodal lines, what you do is that we do a composite plots. So we recombine the information for x1 as well as x2. And as you know that because the mirror symmetry, this plot and in the back side is basically the same, which is just the next Bilayer zone. So when we take the information for particular, when we plot the combine, like I am showing here, first Bilayer zone and second Bilayer zone, just get the information for the mirror symmetries, like as I said here, these two, and make a combine with each other, make a composite plot, which gives clear indication that these nodal loops, whatever we are talking about, they are not independent, but there is a linking formation of the nodal loop. And this we repeat into the entire Bilayer zone along the kx, ky, as well as kz directions, and we form the 3D version of this, how the nodal loops are connected with each other. And this clearly shows you that this is the linking formation, like there is a complex network of the nodal line, and these three nodal lines are the three color code that I showed you in the first figure, where I showed you the Bilayer zone, that there were three color codes. So these three color codes are actually three nodal lines which are protected by the three mirrors mx, my, and mz. Now to get this info also, what we do is that this is another formation.
Excuse me, you have 5 more minutes.
Yes. I have one more slide, no problem. So this is the projection of this nodal ring, like this is a coupled ring, and this is the 2D projection. And when we take this and where we want to observe the contribution for the all nodal lines, what you do is that we take the diagonal direction, which is 111 direction. So this is the 111 direction projection where we can see the contribution from all the nodal lines. As you can see that the linking number which we define is actually the minimal number of the crossing between the nodal loops, and which is actually 2. And because of the three-dimensional crystal, we have the same repetition along kx, ky, kz. As a consequence, we have the linking number of 2, 2, 2 in these compounds. The final plot, this is our final slide also, which is the surface state. So if this is the nodal line or y line, then we must have the surface state. So for that, what we do is that we collect the RPS spectra, which is energy dependent, and we particularly focus into the energy spectra, energy like the incident energy, which is surface sensitive. So in this case, we have focused onto very low energy, which is around 63 eV of the incident photon. And this is the projection of the surface state. So this surface state, if it is a nodal line, you can call this as a drumhead surface state. They actually represent the same thing. But since we are calling this as the Y line, we go back to the notification, the notation, we go back not on the drumhead, but we go back to the mother, the term, which is called the Seifert surface state. So this is the projection. This is the 3D view, and when we take the projection, it looks like this. And this is the 3D view of the Seyfert surface state on the Bilayer zone. And when we take the projection along 111 direction, so this is the projection on the surface states. So this is our experimental data, and this is the theory. As you see that we clearly observe the Seyfert surface states in the experiment. So this is the one-to-one correspondence with theory and experiment, which shows that indeed we have the nodal line which are linked with each other, and we have the surface states, which is the Seyfert surface state from these materials. So this carries a lot of importance for future prospects, like studying this, how this linking number can be, or this linking of the nodal lines can be manipulated, because this is ferromagnet, right? So we can manipulate by the ferromagnetism by external doping or by playing with the crystalline symmetry. Then you can have the topological magnetoelectric effect, or how this linking number can be altered by external perturbations, and we can create the phase diagram, etc. So there is a lot of prospect on this work. So I'll just thank you for listening to me, and these are some funding. So this is my new lab, so I have just certain funding and thank to these agencies. So I stop here. Thank you.
Thank you, Kaustav. It was a really wonderful talk. Very comprehensive work on Whistler alloy, cobalt to manganese. Talk is now open for questions.
So very nice talk, sir. So my question is, when your three symmetries there, I mean the MX, MY, MZ, then three nodal line is there due to this symmetry. Then when you are putting the SOC along the 001 direction, then only the KZ is equal to 0 plane nodal line is survive, other nodal line is break out. My question is that which nodal line you are calling the while loop, because in another plane your nodal line is break out. Then why are you saying this is while loop?
Yes. So in these compounds, I just gave you one example. Let's say you apply the magnetic field and polarize all the spins along Z direction. Okay. But in reality, you don't need to apply any magnetic field, because this is a ferromagnet, right? So you have the internal magnetic field. As a consequence of this internal magnetic field, these nodal lines will already gap out depending on your domain structure. Okay. You no need to apply magnetic field. So it all depends. This nodal line, which nodal line will be protected or which one will not be protected, depending on the spins, which direction it is spins. If, for example, if you don't apply magnetic field along Z direction, just apply magnetic field along 111 direction. Let's say all the spins are polarized along 111 direction. Then all the nodal lines will be gapped out. But what is the strength of the gapping? That is the question. Who will determine the real gapping out or not? That is the strength of SOC. But in this compound, you have cobalt, manganese, gallium, which are really weak SOC. As a consequence, even though you apply the magnetic field along Z direction and all the spins like polarized and it gaps out, in practical it does not gap out. As I said to you, you see our experimental result. Instead of wild points, what we observe is the line node, because the gapping of this wild node is beyond the experimental realization. It is beyond the resolution of the experiments. Okay. So wild lines, whatever we are talking about, the nodes, wild nodes, instead of wild nodes, we have the wild lines, because the overlap lines, the nodal lines, whatever we are talking about here, these nodal lines are the wild lines, because of these are ferromagnet, intrinsically ferromagnet. So we have these singly degenerate bands intrinsic to your system, and like the wild fermion, you have two singly degenerate band which is crossing. So here also you have two singly degenerate band crossing, and this nodal line, it is not really gapped out because of your weak SOC. That is why we are calling this nodal loop as a while loop, and this also carries the surface states.
Okay, I think the point has been made. Shall we go to the next question?
Sir, responding to the gap, there will be some Berry curvature, no?
Yes, that is what I am saying. There is a strong Berry curvature. As a consequence, you see, we have the anomalous Hall conductivity, large anomalous Hall conductivity.
So if there is no Berry curvature, if there is Berry curvature, then corresponding to that, there is some gap.
Yes, there is the gap. but that gap is beyond experimental realization.
Okay.
The gap is too small. That's what
Too
he's
small.
trying to do. Okay, Tanushree, you can go ahead with your question.
Yeah, Kostab, interesting talk. I just wanted to know what are the basic ingredients. It was not very clear to get this while loop. You have broken mirror symmetry. You also have ferromagnetism. So you have also broken the time reversal symmetry. So what is the ingredient? If of course you found it in this cobalt, manganese, gallium, but if I have to think of another compound, what is the ingredient to get a while loop instead of a while node?
So for that, what I feel is that, like, first thing is that you must have the, without SOC, you must have the nodal lines. Okay. Like let's say you don't have any you don't have any magnetic interaction in the material, it's a non-magnetic, you have the nodal line. Okay. Now once we incorporate the spin orbit coupling in the, and also the magnetism in the material, question is that whether these nodal lines, whether it will be there or not. For example, I will give you another example. Let's look into this material, cobalt 3 into sulfur 2. Without incorporating SOC, this also has the nodal line, right? But this nodal line gaps out and forms distinct wild points because you have huge anisotropy in the material.
Okay.
This is cubic crystals and this is hexagonal crystal. By default, you have huge anisotropy in the material, and the spins, it has a like anisotropy. There is a natural tendency for the spins for the easy axis and hard axis, which is absent in this class of cobalt to manganese gallium class of compounds, because these are cubic crystals. So by default, it has the domains formations and it does not have really like the preferred orientation of the spins.
I do understand that. But then what is the origin of the topological character of this line? I mean, this line could be just some trivial line. But there is, of course, as I think you answered in the previous question, there is a very curvature associated with it.
Yes, yes.
So there is a non-trivial topology of this line.
Yes.
And that non-trivial topology is driven by some spin-orbit coupling.
Yes, without spin-orbit coupling, anyway, these topological states will not exist, right? So,
right. So that is what I'm saying. So you need spin-orbit coupling, but the spin-orbit coupling should not be also very strong to gap it out completely.
Yes. So spin-orbit coupling is essential to get the very curvature in these compounds, to get the anomalous Hall effect. But the strength will not be controlled by the spin-orbit coupling. It will be controlled by the crystalline symmetry of your material and what is the like magnetization in the material and how the spins are aligned, and what is the Fermi level with respect to the topological states where it is forming, how far it is from the Fermi energy. So these are the points which will eventually decide whether, even though you have the wild nodes or the topological states in your material, whether it is going to show you in the physical properties or not, like large anomalous Hall, etc. or not. That will be controlled how far these topological states resides from the Fermi energy.
Just another question: is there any other Heusler alloy in which such a kind of wild loop has been found?
You take any cobalt to Heusler alloys, like for example, I can tell you cobalt to vanadium gallium, cobalt to tin CO2 TiSN. So all these compounds, it is already predicted that these will form, but only difference between those compounds and cobalt to manganese gallium is that for cobalt to manganese gallium or cobalt to manganese aluminum, the topological states form very close to Fermi energy. That is why you have so large effect on the physical properties. But for cobalt to vanadium gallium or cobalt to titanium tin, you have the exactly same states, but they are much far from that Fermi energy. That is why the Hall effect, anomalous Hall, or let's say the thermal transport behavior properties are not so exotic. It's just like a normal.
Sorry, I may have to intervene. I think the point has been made. In the interest of time, is it okay, Tanushri, if we move on to the...
Absolutely, because he has already answered.
Okay, thank you. Sudipta, you can ask your question.
Yeah, I have a question that the nodal lines are defined by crossing of two bands, right?
Yes.
I didn't see in your presentation any data where you are showing the energy dispersion of bands, experimental energy dispersion as a function of say angle or K.
Yeah.
Where it is, I mean, you can map out the whole line experimentally. Have you done that?
Yeah, that is also done. That is how we generate these patterns. So these patterns are actually all the crossing like cards like collected together and plot these ones. So these cards, whatever I'm showing, I think
these are Fermi energy, Fermi surfaces.
Yes, yes. These are Fermi surface as well as these cards also. We do energy dependent. Sorry, because of the time limit, I didn't put the slides here, but we have shown that. So maybe you can look
the
into
question
this.
has been answered.
Okay, thank you.
Okay, Swapnil, very quick.
This is also.
Okay, I just have a simple question. The while loop that you're showing, usually the while points are coming with polarity. So what is the polarity distribution of the loop across the loop?
Do you mean chirality?
Sorry, yeah, chirality, not polarity. Sorry.
Chirality, there is a little bit difference from discrete while points and the while lines. So when you have discrete while points, it can act as a source and sink of the while points. You have the Fermi arc, whose Fermi velocity determines whether it's a source or it's a sink, one while point. But instead of while points, here you have the while line. Okay, so the surface state is also not a discrete line like a Fermi arc, but it is a, like you can see here, the Seifert surface state, which is like a drumhead surface state. So there is a little bit difference compared to when you want to discuss about chirality of the while point with respect to while line.
Okay, thank you. I believe the question has been answered. Shivani, very quick. If you have a short question, I'll allow you to ask now.
Sir, my question is, how can we realize the presence of while loops from electronic band structure?
It is from while loop from the band structure is, I'll say, first of all, your approach should be look into the crossing points, whether you have protected crossing points with pi very phase very close to Fermi energy, or it can be away from the Fermi energy also, whether it exists or not. That is first thing. Second thing is that the crystalline symmetry plays a very important role. You look into whether this is a cubic symmetry, like a low crystalline symmetry, so that or it's a high crystalline symmetry, like whether how much anisotropy you have in your compound. That is second part. Third part will be like what is the strength of SOC, whether SOC is strong enough to gap out this nodal line or not. Because you can have a lot of nodal line compounds in the material database. Like yesterday, Professor Barnavik was giving a database, right, where you can go through and look into a lot of compounds in the database, topological database, where there are a lot of nodal lines. Now start with those nodal lines, look into whether they are magnetic or not. If it is magnetic, then whether these nodal lines are protected or not, how they are, what is the degree of protection for that, what is the degree of like the strength of this SOC for those compounds. Then you can get a gauge for whether we can get a nodal line or not, like while line or not in the compound.
Okay, sir, thank you.
I think we will have time at the end of the session also, since we are already 6 minutes late. I will, Aishwarya, sorry, excuse me. You can ask your question at the end, right? I saw your question in the chat box. Probably it will take quite some explanation. So in the interest of time, I'm very sorry. We'll move on to the next speaker. But before that, let's thank Kaustubh for a wonderful talk. I mean, it was really amazing, Kaustubh. Very nice. So I would now like to invite Ajay. Ajay, are you around?
Yeah, I'm here. Yeah.
Yeah, okay, great. So Ajay is from National Institute for Science, Education and Research in Bhubaneswar. And sorry, I don't know what the title of your talk is. Can you please share your start?
Yeah.
Okay, yes, of course, he is the guy working on skyrmions and anti-skyrmions in India. One of the most important people. So he is going to talk about skyrmions in some centrosymmetric magnets. Ajay, over to you.
So I hope you can see my slides.
Yes, we can.
Okay, thank you. I would like to thank the organizers for giving me chance to talk in this interesting conference. As already introduced, so I would like to talk about this scormions in centrosymmetric magnets. So I'll briefly discuss why I have mentioned about the centrosymmetric magnet and what happens, how they are different from the conventional scormions. Okay, before going to my talk, I would like to thank the funding agency like DAE, who is always support us, and then some of the national funding like ACRB, DST Nano Mission, and Max Planck India Partner Group. Okay, so what is scormions actually? So scormions are those are vortex-like objects with a swirling spin configuration. Here I have given a schematic picture of the scormions. So here you can see a bunch of spins. They are coming together and they behave collectively. So if you see the bunch of spins is not randomly arranged or anything. So but they have a very nice arrangement. If you can closely look at the center, the spins is pointing down and slowly it changes the the direction and go to pointing up at the periphery. And if you just take a cross-sectional view of this scormion, and you can see it is nothing like it is look like a 360-degree domain wall with nil kind of rotation. Okay, so why these scormions are very interesting? So they are interpreted as localized spin structure with particle properties, they behave like a particle means they behave although there are thousands of spin, but they behave collectively. They are topological stable against any continuous deformation. Okay, so this point is the most important point why these scormions are so important. That means once this scormion is formed, so okay, so in this talk actually my talk is a little bit different. I am not going to the real momentum space topology. Here I am talking about the real space topology. So in this topology of the structure, the real space structure of the scormion is such that you cannot continuously deform into another object. So either you can find a scormion with this whole bunch of spin, or it can disappear without any deformation. Okay, so they are defined by a winding number. So in the momentum space, you define by Chern number here, winding number. So I will also come to that shortly. And they are most importantly they are chiral in nature. Okay, so since I already told about they are defined by winding number or topological charts. So this is defined by this thing. So I'll just give some examples of winding this different topological magnetic objects or different kind of scormions. So that are found with a different kind of winding number. So these are three examples of scormions people have found already. This is the block scormion. So block scormion means this. If I take a cross-sectional view, this rotation will be like a block domain wall. And nil scormion, similarly, if I take a cross-sectional view, this rotation will be like a nil. As in the previous slide, I showed a nil scormion. The rotation will be like a nil domain wall. In case of anti-scormion, so we have both block and a nil rotation in a single object. So that's why anti-scormion is very special in nature. So how this winding number is defined? So if I take this two-dimensional spin structure and I wrap it to a unit sphere, and you can see they will wrap once into the unit sphere. So okay, so from this we can define our winding number. Similarly, winding number 0 we can define here. Actually, this winding number 0 is defined. Actually, there are two. If I take antiferromagnetic scormion, there are two magnetic sublattices, and they wind opposite to each other, and total winding number can be 0. So they similarly winding number for scormion and anti-scormion can be also 0. And people have also found winding number halves. They are called meron and antimerons. So these are the some of the topological objects people have found. So in the field of scormions. Okay, so why scormions is so important? Okay, so in 2007, Stuart Parkin proposed a new kind of memory device called a racetrack memory, where we can take a vertical kind of or horizontal domain walls and then pass spin polarized current inside this domain wall. Then due to the spin torque phenomena, so this it will spin polarized current will give a torque to this here the magnetic moment, and this domain wall will move inside this device. But it was found that motion of the domain wall requires a large current density, and later when this Scormions were discovered, and it was found that it's to start the Scormion motion we can really need very low current density, and most importantly Scormions are topologically stable. Okay, so and people have already shown that Scormion can be generated and can be moved with using spin current. So here you can see, so we pass this current and we generate Scormion and we can move this Scormion. This is this image is taken in using move. Okay, so what are the ingredients to achieve Scormions? So some of the ingredients what we know in the if we take first of all it should be magnetic material, and second thing if we have magnetic material, so then means my Heisenberg exchange and this time means if anisotropic energy, Zeeman energy all are there. And in addition to that, so to find this Scormion, we need this Gilosinsky-Moria interaction, and that's why to find to get the Gilosinsky-Moria interaction, the system must be non-centrosymmetric in nature. That means it should not have inversion symmetry. The inversion symmetry should be broken. That's the most important to get. So initially when Scormion was discovered, it was discovered in this kind of material where the inversion symmetry was broken. So to get the Gilosinsky-Moria interaction. So what are these most important parameter? We should have spin orbit coupling to get this DM interaction, then broken inversion symmetry, and most importantly, what is the ratio between J and D? If one of these parameters J is very large in comparison to D, then we cannot get also Scormion, because J will dominate and it will always give some collinear, most of the time collinear magnetic state. Similarly, if it may not, but in general J is more larger. But to get Scormion, so J ratio between J and D must be comparable. So depending upon the nature of the symmetry of this material, we can get different direction of the DMI vector, and we can get a chiral cycloid or chiral helix. In case of chiral cycloid, this is called we get generally nil Scormion, and in most of the cases, if we take this bilayer material like a thin film material, we get a chiral cycloid. But because in this kind of material, this kind of DMI is preferred. And in some of the most of the bulk material, we generally get chiral helix. So depending upon that, we can get block Scormion. And as I told, this Scormion, this block Scormion was first discovered in this manganese silicide using small angle neutron scattering experiment, and subsequently the group of Takura in Japan, they performed this Lorentz transmission electron microscopy measurement to show the existence of Scormion in this material in the real space. Okay, so and then those are some block Scormion, and these are some anti-Scormion where we can get different kind of Lorentz pattern depending upon because this in this material the DMI, the supported DMI is it supports the anti-Scormion. Okay, so now I'll go to this my work that we have done recently here in Niger. So I'll show you in some of the recent work on Scormion in centrosymmetric magnet. So when I say centrosymmetric magnet, that means there is no DMI in the material because it does not support the DMI. Then how can we get Scormion in this material? So for that, first of all, we have J, this Heisenberg exchange. In addition, if the material, if we have this dipole means large dipolar interaction and large uniaxial magnetic anisotropy in this material. So what happened in this kind of material? competition between this dipole interaction and uniaxial magnetic anisotropy can give rise to skyrmion. And since there is no DMI in this material, because DMI is the one who is give the chirality in the system. Since there is no DMI, the skyrmions found in this kind of materials, they are generally found like both kind of positive and both clockwise or anti-clockwise kind of both kind of rotation helicity. Okay, so the work so like this. So I'm going to show this work today is like this like skyrmion is manganese for gallium to ascend this hexagon material, and this work is done by my PhD student Dola Chakrabarti. So in this is the material which show like this like a carbomic kind of like structure, and it's so like a magnetic ordinary temperature above the room temperature, something around 325. And so when we did like initial like magnetization measurement like M versus S loop, so we find some signature of like some kind of metamagnetic kind of like signature transition. Then we perform the AC susceptibility first to see if there is anything in the AC susceptibility measurement. And we saw really some kind of cusp in the like, it's not very like, say if you see 10 Kelvin, it is very like continuous kind of behavior with magnetic field. But at like high temperature, you see there is some like cusp kind of thing. And if you take a fast derivative, you see some like there are some transition in this compound. And we know from like our previous work that if this kind of behavior is there, it is already this like known anti-skyrmion system. What I have shown the picture in this material. If we see perform this AC susceptibility, we see exactly similar kind of cost kind of behavior. So this motivates us like to perform like some real space measurement to confirm the existence of skyrmion in this material. Okay, so we perform this real space measurement using this Lorentz transmission electron microscopy that we have also installed here in Azure. So what is this Lorentz transmission electron microscopy? This is nothing so like different from the normal TM. In the normal TM, we have like a pole piece, which like means that is called this like objective lens, where we have a like magnetic field like something around more than 2 Tesla, and you know. If we have a magnetic field of 2 Tesla and if we put a magnetic object, in most of the time it will go to like a field polarized state. That means all the spins will orient in the magnetic field direction. Then we cannot see any magnetic like if we have any magnetic objects in this like material or domain walls or like skyrmions, whatever, because they all will go to spin polarized state. So what we have to do in case of this like skyrmion measurement, so what we have to do is like we have to switch off this like objective lens. So if we switch off the objective lens, then how can we do the measurement? How can we do the focusing? So in that case, we insert a mini objective lens. It is called the Lorentz lens below the sample space, so that the magnetic field from this mini objective lens does not reach the sample specimen. Okay, so in that case, we preserve our like structure, magnetic structure in the material, and also we can focus. All means although this like our like resolution will be lower in this case. And people have done like so it means like this Lorentz transmission microscopy was used in 1980 also to like visualize the domain wall. So you're like if these like electrons are coming like this and spin like magnetic moments are like perpendicular to the direction of the electrons, then it will give a Lorentz force, and from that this name Lorentz like microscopy comes to picture. And depending upon the direction of the spin magnetic moment, so it can divert the spin or it can convert the spin. So around the domain wall, we can get a bright, when it is converts, this beam set converts, we can get a bright like spot. When the beams are diverged, we can get like a black spot. And depending upon that, you can see. So initially people use this method to map out the domain structure in various magnetic. This is the real space image. Okay, in our material, so this material what we prepare is a polycrystalline sample. In the polycrystalline sample, so we cannot apply magnetic field in a particular direction. So what we have to do is first initially we take this material into a SCM where we have EBHD detector, and we find this grain where we need them, like where we can apply the magnetic field like along the hexagonal c-axis. So then we caught that grain using FIB, and then so we performed first like diffraction measurement to see if this grain is really a single crystalline and it is oriented around the c direction, which we got. Then so we started we switch up the objective length, and then in the zero magnetic field, what we did, there are like these are three different images. One is in focus, one is under focus, one is over focus. So in the in focus, generally we don't see any magnetic contrast. Then when we under focus or over focus, so we can see there are some stripe kind of domains in these materials. Then we increase the current slowly in the objective lens. Okay, in the object, because sample is sitting in the objective lens area, so we slowly increase the current in the objective lens so that we can apply some magnetic field in the sample space. Then what we saw, so that this whatever the stripes were there initially, they broke into you can see nice like kind of bubble kind of structure. Okay, and when we increase the magnetic field, they initially so then around 4 kiloastat they start disappearing, and around 5 kiloastat they completely disappears. Okay, so this was with different magnetic field, but the measurement was performed at 100 Kelvin. So we have a liquid nitrogen sample holder for the TM where we can do this measurement. Then so what we did actually, we increase the temperature because this sample is magnetic up to 300 Kelvin. So we increase the temperature slowly. So what we observe around 200 Kelvin. So with this kind of bubbles, we have some different kind of bubbles appears in this system, and around 250 Kelvin, this different like secondary kind of bubbles are more actually. If you see this bubble, okay, let me show you like a image. Here you can see in one area, so there is a black spot in between, and then white, and then here is black. But here, this is a kind completely like circular white kind of contrast. Then inside circular, completely circular dark. Here outside is complete circular dark, and inside is complete circular bright. So why before our work, there were some reports of Fermion bubbles in different kind of system, centrosymmetric system. So what some people say this is like a they say it like in the some paper they say it is a type 2 bubble, and this some paper this kind of spin structure, if you do some kind of like people call TI simulation, they call this a bifermion. Bifermion means this this topological winding number is 2. So this was very conflicting report. Then so what we did next is we did some very systematic measurement. So what is the problem in this Lorentz TM? So since we have to measure this thing exactly, we have to apply the magnetic field exactly along the zone axis, along the 001 direction. So then what happens? So this if you go to low temperature, so there are lots of bending contour comes to picture. The sample becomes completely black. Okay. So we cannot measure anything if we apply exactly along the zone axis. So what we have to do is we have to little bit tilt the sample along some other direction. And when we tilt the sample some other direction, so if we have a magnetic field, then what happens? So we have some in-plane kind of magnetic field comes to picture. You see here, but at low temperature we cannot measure anything at exactly at zero tilting. But at little bit high temperature, this is measurement is done at 250 Kelvin. We can do some measurement at high temp, with zero tilting. But you see when it is zero tilting, you can see all this what about the bubble kind of spin structure. You see they look really like a block fermion, completely bright contrast outside, inside is dark contrast, and or vice versa, because since this is there is no chirality, no DMI, so we expect both kind of helicity in this structure. But interestingly, we only get this kind of fermion. But now you apply little bit of in-plane field, you tilt the sample along the beta direction, and we see what exactly along the direction of the tilting we have like this kind of structure appears. And here we have this one alpha tilting here. Then this like if you see this was in a horizontal direction, this black line, and this black line is now in the vertical direction. And this can be, if you make this like alpha -6 or alpha +6, and this contrast will completely opposite. And we also did like a micromagnetic simulation. Means like what we see when we apply in-plane field along some particular direction. So then what happens, you see these pins actually, so they try to like align a little bit in that direction. When these pins try to align in that direction, so what happens, your magnetic contrast actually changes. At the zero magnetic field, so we have very nice like zero tilting, we have very nice like image. So like so it all looks like a block experiment kind of thing. But when you tilt a little bit in along the plus alpha or minus alpha, so our simulation and our like image completely matches each other. So if we like this is the like simulated picture for this one, you see simulated inside here inside bright, outside bright, here it completely matches here with this picture. So that here from this we confirm that when we like apply little bit of in-plane magnetic field, in this picture we have outer plane magnetic field along the 001 direction. But when we tilt little bit the sample, so for a better imaging or something, so then we give some in-plane magnetic field to the system. And in that case, the in-plane spin like magnetic moment, they orient at a particular direction, and that breaks this like blocks fermion or something, and it become a trivial bubbles, and so we get like this kind of a spin structure. And from our measurement, we confirm that these are not type bifermion or like where this like topological number is 2 or something. This is indeed like this is the blocks fermion, but due to applying this field in some little bit tilting direction or some in-plane field, so they convert into this trivial bubbles. And we also did some like I finished. This is my last slide. Okay. Yeah, means like so you also perform this like so we see how magnetic anisotropy is important in this material. But we see this fermion number or something is very much like related to the magnetic anisotropy in the system. So when this magnetic anisotropy is very like the highest, we have the highest fermion number. So that means here in this material, magnetic anisotropy is the most important parameter to define, to generate fermions in this material. And also we did magnetic simulation to support our result. And we did we draw like a phase diagram and to show like that where this fermion exists. And indeed we can find from 100 Kelvin to 300 Kelvin this fermion phase. Okay, so this is my last like conclusive slide. So we have observed near room temperature fermion lattice by using low temperature Anomalous transmission electron microscopy. So we have observed also switching between the topological fermion and non-topological type 2 bubbles with non-zero in-plane magnetic field excitation. And we support our results with like a simulation. Our results categorically suggest that the type 2 bubbles are not the fundamental magnetic structure, rather by a byproduct of the magnetic fermion in the systems. With this, I would like to thank you.
Thanks, Ajay. It was a very nice talk, and I really appreciate the work that you have done. The talk is now open for questions, and I already see a hand raised. Surjit, you can go ahead and ask the question.
Ajay, very nice talk, and it's a very important work. And I have a few questions about. First thing is that the bubbles seem to form a nice lattice.
Yes.
So is there a understanding why it should form a periodic lattice? This is first question. Second question is that this is a technical question, that physically in the real space, where are they located? Surface of the your sample or inside your sample?
I'll answer both the question.
Yeah.
So first of all, why they form a lattice actually? So if they are topological stable, so they have always actually attraction or repulsion between them. So depending upon like what is the space what is the like periodicity or something. So we have like we have a fixed Fermion distance. So they have always some repulsion. So they have always a repulsive force in between. So that itself gives like this arrangement. So if you take any like Fermion material, so this like attraction and repulsion, they form a lattice, and generally hexagonal is the closed stack. And but if you have like a different kind of symmetry, so we can get also square lattice. All we have seen in different material, depending upon the anisotropy of the material, we can also get a square lattice. And about the second question, why the surface or bulk? So they actually they're throughout this throughout the sample, because this is the TM we are measuring in the transmission mode. So transmission means we are looking throughout the sample. So this is like we can imagine like they are like a cylinder. So throughout the sample.
I see. Just a short third question. The bright regions mean that the spins are aligned in plane, and the dark regions out of plane. Is there something
No,
like
no. The bright region where actually this like here, okay, I have not drawn this. Like if you can see, okay, let's go to the simulated picture. So here, so means like maybe not Lawrence, this one here. So this bright and dark constant comes when they are like constant, like constructive, like beams are converging or diverging. So depending upon how this electrons are electron beam is like diverging here. Sorry, how the like electron spins are oriented. Always they are in plane. If they are out of plane, we don't get any like deflection, because this is Lorentz deflection. They are always in plane, but how they are oriented. Okay, depending on the orientation, we can get actually this kind of like so the most important like example is this like anti-Fermion. You see bright, dark. And because due to this, I have not put this schematic because I am not talking about the anti-Fermion. Depending upon the spin structure, we have a converging convergence of the beam or divergence of the beam, but always it is in plane.
Okay. Thank you.
Thank you. Are there further questions?
So we have a question.
Okay.
Hi Ajay, nice talk. My question is that I didn't understand what is the sample. It's a bulk.
So it is a bulk sample, but to do the TM measurement, we took this bulk sample in our FIV. We found this direction, like a particular grain what we want to measure, and we cut that grain to something around 100 nanometer thick.
Okay. Now my question is that related to the device structure, like Parkin's idea, what you talked about, right?
Yeah.
So first thing is that do you see any signature in the transport? Like if you just do a 4-terminal resistance measurement.
Yes. The transport people do in the mostly Hall effect measurement. Okay, but that actually is very crucial. But that depends upon the size of this fermion. So if you measure the transport in this material, you may not measure it properly, because our sensitivity of our PPMS ACT option is not so good. But if you measure very something around nanometer sensitivity, we can measure. So if your Fermion size will be very small, something like 10 less than 10 nanometer or something, you will see nice topological Hall effect in this meter, because they are topological stable, and due to that, so you get a topological Hall effect in the Hall effect measurement.
Sorry, sensitivity means you mean measurement sensitivity.
Measurement sensitivity, because since these are actually large Fermion, and so you're this topological Hall effect is directly proportional to your Fermion size in this material. That there is a relationship, and since in this material it is very difficult to measure the topological Hall effect, but we have published some other material like manganese to nickel gallium, where we express Fermion size is very small, and we get very nice topological Hall effect there.
So if you just apply current, this will move using a Lorentz force kind of force, right? So it will move.
No, the moving of this Fermion, it is different. This is spin torque phenomenon. The topological Hall effect comes when the electron moves inside this Fermion. It actually due to this Hertz coupling between this electron and this inside the spin. So it rotates, like it get a very, it again comes to this very physics. It gets achieve a very phase, and that gives the topological Hall effect.
Okay, thanks. I'll discuss with you later. Maybe some other question. Yeah.
Nisha, you can go ahead.
Sir, I have a question that, sir, how you have differentiated the bubble from this fermion on the basis of simulation by topological charge calculation, we can get idea about whether it is bubble or fermion. But from the experiment, sir, I did not understand.
From the experiment point of view, so first of all, from the experimental point of view, from like you can see, so what you can do, so to confirm whether it is a topological like bubbles or like a fermion, of course, like fermion, okay, so when it is fermion, it has a topological number, and we have like some kind of fermion Hall effect comes to picture. So you have to do like this like little bit dynamic study, okay. And like to understand, we always do some simulation whether they are fermion. If it is fermion, you can calculate this, like what is the topological number. You can take this spin structure and see with this simulation we have got both the like bubbles kind of thing and fermion, okay. And if we do this like calculate the topological number what I defined here in the first slide, we exactly get one from this, like here winding number. We get 1 for this structure and we get 0 for this structure, for this kind of structure.
Yes, sir. From simulation, I understand, but sir, from the Lorentz team experiment,
from the Lorentz, as I told, for the Lorentz team experiment, means how can you say that this is like exactly? You have to do means a corresponding simulation, okay. So initially when this Lorentz TM was done, so that was also means like people perform some simulation that to say that this is a like a fermion. Then people did in the Lorentz TM, if it is a fermion, it will have fermion Hall effect, okay. Then people did also that fermion Hall effect thing. Then they saw this fermion is moving towards the edge of the sample little bit, okay. And from that they confirmed this is a topological object.
I think Ajay, she wants to know if one has
from the static measurement, no one can say. From the static measurement, no one can say.
To see the spin texture, if one has to see how
from the static measurement, either you have to do corresponding simulation or you have to do some dynamic measurement.
It be done using neutrons.
Neutron also, that is also in there. Means like topological, whether it is topological not neutron also cannot say.
Okay.
But Hall effect measurement is a good measurement. Because topological Hall effect comes only if it is topologically trivial, non-trivial.
Okay. All right. Thank you, Ajay. I have a very quick question. So this is a centrosymmetric. So DM is out now. So since DM is out, you said we have to bring in something which is long range and which can, compete with the Heisenberg exchange. And your proposition was it should be the dipole-dipole interaction. So, I mean, at such high temperatures, would the dipole-dipole interaction be relevant? Because, I mean, even for
until like it is magnetic, so dipole means in a particular thickness region, it will be always relevant. If you take a bulk sample, it will be irrelevant. But until it is magnetic, like it will be always relevant. No?
So what I remember from the studies of spin ices is that between two dysprosium spins, 10 bar Bohr magneton, the dipolar interaction is very weak. It's about 1 Kelvin, so the order of 1 K.
Spin ice, I think this is a
spin ice example I gave just to just as a reference that dipolar
are they like magnetically stable, mean ordered until room temperature? Because as I know, this spin ice system all are like
just an example. I mean, if you take two very large
if it is like magnetic, there should be dipole interaction always, right?
Yeah,
like room temperature or whatever.
Of course, there should be, but the strength of dipole compared to the Heisenberg interaction is
no, not here. It is not with Heisenberg. It is with universal anisotropy.
Okay. All right. So I think we can.
Surjit, there are a few questions from. Do you have questions?
Yes, I have.
Sorry.
Hello. Thank you for nice talk. The picture you have shown, or people usually used to show for fermion, Is there any domain wall? I don't think it is a continuous evolution from one point to another point, like spin wave. So how can we define domain wall? Continuous change. It's not a like anti-ferromagnet or ferromagnet that drastically it will change from one point to other point, separated by wall.
Okay, so here actually, so there we are not any. So we're not talking about any domain. Okay, so if you take this like stripes here, what do you see in this like slide? So we have stripes actually. They are actually also stripe domains. If you go from like so like one stripe to another stripe, it spin always rotates actually. You can imagine here they are stripe domains actually.
Okay.
But sorry.
I have a quick question. That's a nice talk. So if I measure all measurements on the bubble system and Fermi system, what would be the major difference that I would see?
Sorry, what would be the difference we should see?
Hall effect measurements.
Yeah, so in the Hall effect measurement, okay, first of all, this like to measure like a sizable Hall effect, this Fermi size should be small, because in this system or anti-Fermi system, what means like we publish nature, we cannot measure the Hall. Means it is Hall signal is so small that we cannot measure. If it is very small, of course we can measure, and in that case we will get like a topological Hall effect signal. But if it is bubble, trivial bubble, we should not see any topological Hall effect.
Okay, we should not see the topological signal. Okay, thanks.
Yeah, so maybe a last question. In your this bubble, because you don't have DMI, so do you expect any winding number here?
Yeah, no, as I told you, winding number is there, but you see we have both winding, so both chirality. If you see again, if you since there is no chirality, we get both. But winding, if you take the winding number of this one, this one or whatever, this will be always 1. Okay, but here it will be 0. But here it will be always 1. But it means since we do not have DMI, which gives a particular winding like chirality, we get both the like chirality here.
So that's why you are telling that because both the chirality will be there, you won't need topological Hall. It will be 0.
No. Okay, so. Okay, so okay, so when you like, if you can stabilize one of the chirality, okay, then you will definitely get topological Hall effect. But what I was telling is, if you have this kind of structure where it is topological trivial, you won't see any topological Hall effect. I
think it's more related to the size. That's what he is trying to say.
Size is a different thing, but in this case also, if we have a smaller size. But if we have this kind of bubbles, we should not see any topological Hall effect. But here, if we can also stabilize one of this chirality, we will definitely see topological Hall effect.
So it is directly related to the number of they are small, so you have large.
Directly related to the number, right? There is a relationship between the number of this fermion and density of this fermion and topological Hall effect. Yes.
Okay. Thank you. I think then there are no more questions from the offline.
All right.
Yes.
Okay, so let's thank all the 3 speakers. It was a wonderful session, and I feel very nice that I got to chair this. So
thank you.
Thanks to all 3 of them. Over to you, guys.
Thank you, Professor Surjit Singh, for chairing this nice session. So now actually we'll break for lunch, and we'll have a poster session which will start from 2 o'clock, 2 to 3:30, and we'll have 5 posters which you can see on the screen. So please interact with these speakers who are presenting their posters. So okay, then with this we'll break for the lunch. Thank you.